Okay, so the first time I did this was uh the day after everything was shut down for COVID.
Oh wow.
I had been doing exclusively in-person classes at local community college and whatever other room I could find, and um, typically had 20, 25 people at most. I think once I had 35. And then everything shut down, and I was supposed to be teaching the next day.
Wow.
So I said, "Oh my God, what am I going to do?" So
Yeah.
I ran out to Office Depot, and I got myself a whiteboard, some whiteboard markers, and a camera, and a light. And I basically did the class for the first time in front of a camera.
Wow.
And I
Oh,
ended up
you're
so I ended up with like 9 people, 10 people during that class. But it actually worked out really well. We we managed to get people licensed at a local testing session because it was still local and we did it outdoors. But then everything went remote. And now if anyone's worried about taking an exam and finding an exam to take, you really shouldn't be. Has everybody looked?
I
Every
did a little bit of looking, yeah.
Okay, so if I pop this up, there's on Ham Study, find a session. See this remote? This is just today.
Wow. Yeah.
This is tomorrow. And these are basically you join them over the web. They check out your room, you sign up, you have all your documents. This is Labor Day.
Yeah.
Tuesday, Wednesday. There are a lot of people who are very retired for whom giving exams is kind of like a part-time job. You don't make
Yeah.
money at it, but it's certainly doing a community service. You will have no trouble finding an exam to take either in person or online.
Hey Scott, this is David Brown. I just want to say thanks to my computer sits under my monitor, so I don't have my camera available.
Okay, well, you still got audio.
Thanks.
Thank you. Oh, wait, hold on. That was echo. Do that again. David, do that again.
Oh, he muted himself.
David, you still there?
Yeah, I'm here.
There's a
That
little.
echo sound was my son-in-law in the background. He's on the class too.
Okay, all right.
Testing audio.
Testing. Sounds good.
I'm testing my audio. This is Jamie Waterman. Good morning, everyone.
Good
Morning.
morning.
5-9.
Thank you. Better go ahead and
This
mute
is
again.
Ron from Maryland.
Where in Maryland?
Prince Frederick on the
Prince
Chesapeake Bay,
Frederick on the Bay. Okay. I'm trying to think.
K3CAL,
Is that Talbot County?
Calvert,
Calvert. Okay.
south of Annapolis.
Oh yeah, yeah. No, I know exactly where it is. It's the thing that looks like a little hook.
Strip, like a
Yeah.
like a uh, prime
I
rib.
I've been to Calvert Cliffs nuclear reactor.
Oh yeah, right down the street.
Hmm. For 40 something years, it's been just chugging away. Yeah, I grew up in Gaithersburg, Rockville, Silver Spring, Laurel, College Park, Burtonsville. So that was my stomping ground for a lot of years.
College Park, the
I
VU.
went. I'm a Terp
So am I. Congratulations.
class of
83.
80, 90.
Cool.
Electrical engineering class of 1990.
Gotcha.
And then master's degree in 95.
Damn.
So, and do you have a fan on in the background?
No, sir.
You do?
Not
No?
me.
Okay. I wonder if that's from here. I have a fan, but let me see if that's mine. Nope, everybody hear that? That's not my fan.
There's not. There we
It's off
go.
now.
Okay. But it wasn't from here. I think that was somebody's background. Can everybody believe it's football season already?
Yeah.
Absolutely.
Uh, oh,
Yay.
it came back, and now it's gone. Oh, all right, it's 8:58, and so I don't know how many people are going to be here. I when I see that many people sign up on the roster, I had 177, by the way.
Needs a few toroids or chokes on that RF.
The question is, where's it coming from?
I actually thought you wouldn't have that.
Well, it's not from me because I muted myself.
I'm also hearing it now. I wasn't paying attention to it, but yeah, but it's not that bad on my end.
Mildly annoying. Not the worst thing in the world.
I can hear it too, but it's not that bad on my end.
So let's look and see who's got their microphone open. Oh, that did it. Whose was it?
I think it was Hope and Heather.
There. Sounds like it was Hope and Heather.
It's
Yep.
our ice maker, I think.
Your ice maker. Okay.
Yeah, sorry about that. If it's annoying, I can set it off.
Well, no, I mean, actually, and most of the time, everybody. Okay, so, oh, it's 9 o'clock. Okay, let's go. So I'm Scott. I'm recording, and sure, why not? Um, and one thing I'll say right from the beginning is that I I don't always look for people to have hands up. Can I turn on transcription? I don't know. I,
Real quick, captions look to be on. You have to click on more all the way at the right, and there should be a little caption
captions.
tab.
Okay.
And this is it looks like it's on for everybody because I was just able to turn it on just to test it
Okay.
out.
All right, cool. Okay, so let's see. The first thing I'm going to say is that I don't always look for hands being up. So if you want to say something, keep yourself muted most of the time, but then unmute yourself so I can hear you if you want to just cut in. And now, if you're going to do that like every 30 seconds, it's going to break up the flow of the class. So don't do it every 30 seconds. But, and the other thing is if you have a barking dog, please mute yourself because that punches through really well. Dogs are great for that. And I may have a barking dog here from time to time. So yeah, I know the feeling. Um, So let's see. Good morning and thank you, everybody. It's good to see everyone. And the first test, and I hope everybody passed, was figuring out time zones because the class starts at 9 o'clock Pacific time, which is noon on the East Coast. If you happen to be in the Philippines, I think it's like tomorrow sometime early in the morning, or no, late. No, it's still today, but it's late at night. So, or is it maybe 2 in the morning there? I don't know. Something like that. Anyway, my name is Scott. My call sign is N7JI. That will mean more as we go along. And this is a class on radio and getting your technician class license. And one of the first things that somebody will always ask in class is, well, are you going to teach us how to use a radio? No, I'm going to teach you how to use radio. I'm not going to teach you how to use a radio. That is up to you to figure out how to use a radio. Although I can help you, that is not the function of the class. So if we start looking at the whole purpose for this class to exist, we have to start looking at the whole purpose for amateur radio, right? It's also known as ham radio. There are many services, different radio operators use different services. For instance, this right here, this is known as a family radio service or FRS radio. There's also something called a GMRS, which is General Mobile Radio Service. There's also something called MERS, which is a multi-use radio service. Those are all either just pay for a license or there is no money in exchange in getting and using a license. Those are what I would call um, those are what I would call appliance operator licenses or appliance operator radios. They essentially do have some frequency agility, which means you can change the channel that they're on. You can do certain things with them, but they are limited. They have a distinct purpose, which is communications, right? That is what they're designed for. However, they're not designed to be used for what they're not designed for. They are user things. So like it is not essentially this radio is a mostly non-programmable, non-controllable black box. It has a couple of buttons on it for changing the frequency to different channels. It has 22 channels and 38 tones, and it has this push to talk button on the side. So what can you do with it? You can change channels. You can hit the push to talk button and transmit. It's essentially a black box. It's a communications black box. Your cell phone actually has somewhere between 4 or 5 radios and 4 or 5 antennas built into it. This is a communications black box. It's got a lot of cool stuff on it, which we can do with the screen. We can program it because it's got a really powerful computer in there to do lots of things. But essentially, fundamentally, it is a black box that communicates on a network full of black boxes. Amateur radio is basically the license that gives you the permission to work on and goof around with all the stuff that is underneath that. Essentially, it is the guts of what makes radios work. And so the question then becomes, well, why do we need a radio license? And personally, it is not up to me to decide how you're going to use the license, but the license permits you, for instance, to build your own equipment. I don't care. The FCC doesn't care if you're never going to do that. The license permits it. If the license permits it, you have to understand it, which means you have to take an exam. The other thing we can do, for instance, is not only build a radio, but this is a fixed antenna. This antenna does exactly what this antenna does. It's a very small antenna. It has very low gain. This radio can put out a couple of watts of power, or in this case, it's about a half a watt, into this little antenna, so you get what you get. When you start getting into amateur radio, okay, so this is a 5-watt handheld. This is essentially a black box that is a Yaesu FT60, which you purchase. Now, one thing I can do with this, for instance, is I can take off the antenna. I can hook up this radio to any antenna I please. So the point of that being, well, okay, if I want more gain, which is something that we're going to cover in class, I can remove that antenna, hook up this antenna port right here to a big antenna. I can hook this up to a 30-foot dish if I want to and concentrate all my energy in one direction. I can also decide that 5 watts is not enough power, and I can take this off and hook this to an amplifier, which you can build or buy either way, that can amplify, let's say, a 5-watt signal and make a copy of it that is 1,000 watts. Because we are legally permitted to transmit with up to, on most bands, 1,500 watts of RF energy. And then you decide, okay, well, what antenna do I want to hook that up to? Well, I want to hook that up to, let's say, a 30-foot dish antenna. So now you're basically taking this radio and experimenting with it and hooking it up to a 1,500 watt amplifier and then hooking that up to a 30-foot dish antenna. Is it legal? What do you think, everyone? Is that legal?
No.
Oh, it is. Absolutely. That is covered under your license. I mean, if I want to take this radio right here and hook this up to an amp and hook this up to a huge dish antenna and point it at the moon, and so that I can talk to people bouncing signals off the moon, perfectly legal. So why do we need a license? Okay, because now instead of a little 5-watt radio, we have a 1500-watt amplifier, and we have a, let's say, 30 dB gain antenna, which means that your effective radiated power is now 1.5 megawatts in the forward direction. What happens if you take that and instead point it along the ground and point it at somebody's house? What will happen to the people in that house?
Probably, yeah. Probably
start to
their
cook.
electronics.
It generates heat, and you can
Could be a
start to
little warm.
really hurt people. Yeah. So why do we need to get a license? What is the point of all this? Essentially, we are given an immense number of privileges, even if you never plan to use them. I don't care if you never plan to use them. The FCC doesn't care if you never plan to use them. There are plenty of things that you can do with other services which are canned, right? If you just want to use ham radio for replicating those, that's fine, right? The FCC doesn't care. That's your choice. If you want to take that same license, which is the same license, and do all these other things with it, the FCC also doesn't care so long as you have the license.
Hello, hello.
Yep. So all that being said, that is why there is such a thing as licensing. That is why this exam is not just like, open a book and look at it for 15 minutes and go take the test. Because with the privileges afforded by an FCC license like this, you can do a lot of damage, right? You're allowed to build a 1500-watt amplifier. That might use vacuum tubes that have a 3000-volt power supply to generate that much power.
Here's a question.
Mm-hmm.
Okay, isn't the technician license limited to 50 watts?
No,
What is the limit then?
1500 watts.
1500 watts?
Uh-huh. Yep. It is limited to 50 megahertz and up, plus some bands below that, frequency-wise. But you are allowed to run 50. Like, if you want to build with a technician license, you're let's say, here's a good picture of here we go. Here's an EME station. Okay, so let's say that you decide that you want to get a technician license, and okay, so let's say that you have a technician license, and on, notice, 144 megahertz, all this will start to make sense. This frequency is covered with full privileges for the technician class license, and you want to build this amplifier and drive it with a radio, and you want to build this antenna array. Perfectly legal for a technician to do. So, given the fact that you can build that system and actually put it in use, that is why I don't care if you're only going to use it for operating a handheld during emergencies. Then, basically this license covers a lot more than just operating a handheld during emergencies. It essentially is a license to experiment and do all kinds of cool things, whether you're going to choose to do that or not. And that's why there is a class, and that's why there is studying, and that's why there is an exam. Now, the other cool thing about it is that, with the exception of there being a $35 licensing fee charged by the FCC to process your license, and depending on where you go, the process of taking an exam costs anywhere between $0 and $15. You get your license for 10 years and there's no fee. On the other side of it, it's basically a non-commercial license, which means you're not allowed to do anything like encryption, and you're not allowed to make any money using it. Essentially, it's a practical academic pursuit. Now, I will say that I know that there are some teenagers in here. And one of the cool things about this is that when you get to the point of being done with high school and getting ready to go to college, you got yourself a ham license. There is a lot of money in the form of scholarships available to active college-bound hams. Like a lot of money. Some big, fun scholarships. Um, my daughter has her extra class license, and she got licensed when she was 17 and became active. She's actually going with me to Wallace Island in the South Pacific this fall to operate along with 4 other friends. It's going to be a lot of fun. Um, over 4 years at the University of Oregon, she was active in the radio club, and completely independent of school, she got $60,000 in radio-based scholarships over 4 years. So that's why, this is, you have to prove that you actually want to go get a license. But once you do that, you can take that license, use it, and then people will basically are kind of like pre-screened for getting scholarships, which is kind of cool. All right. Any questions before we get going?
So, question one.
Yep.
Back in March, the new appointed leader of the FCC by His Majesty.
Yep.
He was talking about doing away with fees. You heard anything updates on that?
Nope.
It's just
Nope.
dead
We're still
fish in the
paying.
water.
We're still paying.
Oh, I know we're still paying now.
I honestly think that if there are fees that they can collect, they will collect them. There used to be no fees.
His first term, they didn't.
Yeah, but then they did.
Oh, that's when Joe
that
came in.
actually that was changed by the Ray Baum Act, and that was across the FCC and lots of other groups, lots of other or agencies as well. And
Okay.
I don't see it going anywhere.
Okay.
We're used to it now.
Just quoting the news.
Yeah, I mean, I'd love to see it go away, but I don't see it happening.
Well, they were also talking about licenses too.
Yeah.
That was a rumor that people were jibber jabbing about. They were just off the end on that one, especially the amateurs down here. We're local around the District of Columbia, and they were just going ape shit. Sorry, my French, but they were going crazy. They're like, "You got to be kidding me! What have we worked for all these years?"
Yeah. Well, we'll see. Hopefully, there's 750,000 hams in the United States.
Yep.
So, all right. Other questions before we go? Okay. When you say focus on test, please. Well, I will tell you honestly that I focus on radio theory. Howard, you there? Oh, you're muted.
No, I am. I just, you have a lot of material to cover, and I just don't want this to turn into a political.
Yes. Okay, but I will say a big part of this, and actually this is a good time to mention this, that okay, one of the things that everybody has the book, which is the no nonsense guide, which I sent to everyone electronically. I can't make you study, right?
Yep.
I can't make anybody study. What I can do is I can teach you the basics. I can teach you all the underlying theory, which is really, really, really helpful to understanding exactly how all this goes together. But when it actually comes to getting ready to take a test, you need to get 74%, but I can't help you. So I just went through an experience teaching a bunch of 11 and 12-year-olds, and I told them the first week of an 8-week class, I can teach you everything I know. And I know quite a bit. I mean, I've been doing this stuff for a long time. I got a master's in electrical engineering, and I see things from a systems point of view, as opposed to just like, a very fine-grained point of view. And I cannot make you study. I can't force you to do anything. If you don't work at it on your own, you will not pass. This is something that absolutely positively has to be something that you're going to do on your own and spend time doing it and get ready for. Unless you've got a degree in electrical engineering already and you already know half the material because of your engineering degree, this is actually going to be work. It's very, very inexpensive as far as what you get, the things that you get for the license, the privileges that you get are very, very big, but the actual process, instead of money, it's going to take your time. So everybody just prepare for that. And hopefully people have looked at the book. The sooner you start looking at the book, the sooner you will be ready to take your exam. Once you get your exam, once you get your license, that's when you are actually beginning to really learn stuff. Up until that point, all the stuff I teach is academic. Once you get your license and you get on the air, then you actually start learning because it becomes hands-on and real.
Mm-hmm.
So let's go. All right. So here's the first thing. I don't start at the beginning of the book. And the reason I don't start at the beginning of the book is because the book starts on electronics, and electronics is not where this whole thing begins in my mind. So I start somewhere in the page 30 area, and then we double back. So what I'm going to do first is I'm going to put up this whiteboard. I hope everyone can see it. Can everyone see the whiteboard?
Yes.
Okay. Okay, here we go.
Yes, I can see the whiteboard.
All right. And I don't know why I'm seeing all these thumbs on my whiteboard. All right, here we go. So the first thing we're going to do is I'm going to draw a circle. All right, everyone see the circle? Everything begins with a circle. Bet you didn't think we were going to be doing trigonometry today. But it's essential to understanding where all this comes from. So we're going to take the circle. We're going to give it a radius of 1. And by the way, nobody's left class yet, so that's a good thing, right? It didn't scare anybody away. Okay, we're going to give it a radius of 1 unit. And how many degrees are in a circle, everyone?
365.
I hope it was 360.
360. I get
Okay.
it.
So here, and we start here on the right-hand axis. As we go around in this direction, our angle increases. So counterclockwise. No, I don't know why it's counterclockwise, but that's the definition. Up here is 90 degrees. Over on the left-hand side is 180 degrees. And down here is 270. And when we get back to the 0 point, we've gone a full circle, which is 360 degrees. Okay, so now what we're going to do with this is take that circle and we're going to draw a couple of things. It's a unit circle, so how far left and right can we go if we're riding on, let's say, a car on this circular track? How far left or right can we go?
1 left or right?
1 left or right. Okay, this is the positive side and this is the negative side. So at the 0 angle, we can plot, we say we're at +1 right up here. Down here, we can go all the way down to -1. Well, if we were to plot our horizontal position based on our angle, we would have some interesting points. We have 0 and we have 90 and we have 180, 270, and 360. As we plot those, we can now show that our position, left or right, makes a shape that looks like this. This is a function called the cosine. As we do that, we can decide, okay, well, instead of left and right, now we're going to look at up and down. So how high can we go and how low can we go?
Same, 1 and 1.
1 and 1. Okay, except that at the beginning, we start at the 0 point.
Mm-hmm.
and we go up to 1 at 90 degrees, and we come down back to 0 at 180, and we're at -1 at 270 because we're underground, and back up to here at 360.
You lost your audio, Scott.
Yeah, you did. I sat on my microphone. I sat on the plug. I got to hide it from myself. Okay, so what do you notice about those two waves?
They're slightly offset from each other.
They're offset from each other, but they're the exact same shape, right?
Right.
Okay, so these are known as cosine and sine waves. Those are the cosine and sine functions. So we can do a few different things with these. Okay, so let's go back to our circle. And we're going to add another function to this. We're going to say that we have one revolution, one full trip around this thing is known as a revolution. Okay, now what are some things we can do with that dot, that car on that track? What are some things we can change?
How fast it spins?
Yeah, okay, so we can change the speed. What else can we change?
Start and stop.
Yep, we can start and stop. We can also make bigger and smaller circles if we really wanted to.
Okay.
Right? So that would be the amplitude, which is the size. Okay, so how would we measure our speed?
And revelations per unit?
Yeah, okay, and what's our usual unit of time?
Hour?
No, we
Second?
use seconds.
Okay.
Okay,
Yeah.
so time is always in seconds. Okay. So if we were to speed up and make it and change this to 1 rev per second, we set that as our baseline. How long would it take for us to make this entire pattern over here?
1 second.
1 second. Yep. Okay. How about if we were to make this 10 revs per second? How long would it take for us to make that pattern?
1/10 of a second?
A tenth of a second.
Okay.
Because we'd be going around 10 times per second. Well, okay, so what we have here is an inverse relationship. How about if we were to go around 100 times per second? How long would it take for us to make that?
1/100th.
It would take 1/100th of a second.
Mm-hmm.
How about if we were to change that and make this 1,000,000 revolutions per second?
Mm-hmm.
How long would it take to
1
make that pattern?
Be a megahertz.
1/1,000,000th
Mm-hmm.
of a second.
Mm-hmm.
Okay, so we have an inverse relationship here. This is known as the frequency, and this is known as the period. We use the little letter F for the frequency, and we use the big letter T for the period, because that's based on time.
Okay.
Okay, so frequency is basically, the units of frequency is things per second. That can be somebody clapping their hand. It could be any number of different things. Something happening per second. This is the period is in seconds. So we have a name for the frequency, and it's called the hertz. Okay, so when something happens 1 time per second, we give that a frequency of 1 hertz. When something happens 10 times per second, we say it has a frequency of 10 hertz. Something happens 100 times a second, it's 100 hertz. 1,000 times per second is another name, and we start using, because that has a lot of zeros, we do a substitution of kilo, and that's 1 kilohertz, and so on and so forth. And we're going to get to those units a little bit later. And the reason we do that is to avoid having all those zeros to keep track of. All right, so now we're going to start with another drawing. We're going to take that circle, and we're going to start at our 0 angle again. And we're going to have our 90 and our 180 and our 270. Okay, what happens if we go the other way? Well, we said that this is the positive direction. This must be the negative direction. This is negative 90 and negative 180 and negative 270. Are they not, do they not all reference the exact same points?
Yeah.
They do, don't they? So if we were to draw that sine wave, let's look at the vertical displacement, which is the sine, it would look like this. And notice that it repeats. And the reason it repeats is because it exists the same here, as here, as here, as here, and here. These are all the exact same point, just given a different angle. This is 0, this is 360, 720, 1080, negative 360. They're all really the same. So that circle, that point on the circle keeps going around and around and around in both directions forever. When we take a look at just one period, we're basically ignoring all the rest of this stuff. Just being able to characterize what it looks like for one period. Okay, so now what we're going to do with that is erase all this junk. And we're going to take this circle, and we're going to now imagine that this is a bicycle wheel. No reason not to, right? Could be a car tire also. So now we're going to take this bicycle wheel or car tire or whatever we decide to call it, and we're going to start rotating it so that it's getting closer and closer to being edge on. So we're looking at it like this. It's getting like that and like that. And eventually, when it's completely edge on, what are we going to see?
Straight line.
Straight line up and down. Now, what happens when that point continues to go around the circle in this direction? What are we going to see? If we're looking at it edge on, we're going to see it just goes up. And after that, it just goes down and then back up and back down and back up and back down. If we have a frequency, let's say of 10 hertz, how many times per second are we going to see it move up and down?
10.
10 times, exactly. So we're going to see this dot basically do this. Go up and down and up and down and up and down, back and forth, back and forth, back and forth, in an endless pattern. All right, so the next thing we're going to do with that is we're going to take that up and down pattern. So here's our circle again, which has gotten uglier. We're going to take that circle, do this, and then turn it on its side so it just basically looks like a point moving up and down. And now we're going to take this bicycle wheel, which is turned on its side, and we're going to move it in this direction at a constant velocity v. So we have a dot which is moving nothing but up and down, but now we're moving this dot horizontally as it's moving up and down at a constant velocity v. What is that going to make the dot look like?
That same sine and cosine, right?
It will, because it's a sine, it's going to basically move it at this velocity. But
Right.
now, instead of it just being 0 to 360 degrees over and over and over, we have this thing called a velocity. The whole thing is moving to the side, and it's moving to the side at a speed that is defined by, let's say you're holding a bicycle wheel and walking. How do we measure our speed? What do we use? What units?
Would that be revolutions per second still?
No.
Meters.
Meters per second, because it's a distance. So we can do feet per second, we can do miles an hour. The most common one to use in the metric system is meters per second. Okay, so now we have a couple of different things to look at here, because we had this thing, this dot going around, and what did we call that frequency? That's measured in hertz,
Oh, yeah.
right? And that's our frequency measured in hertz. And what are the units of hertz? It's a thing happening per second. That thing in this case is one wave being made, or one revolution of the circle. Okay, so excuse me.
Would that be a wavelength then?
Well, we're getting there, because math is math, and I can do all kinds of cool stuff with math because math is cool and I can do things with it, because there's nothing that says that I can't. I'm going to define a new thing. Notice that we have per second and per second. I am going to say, that's interesting. I wonder if I can do something with that. So I wonder what would happen if I divide V divided by F, if I get something interesting out of that. Well, I get meters per second divided by things per second. And in this case, it's a wave. That's the thing. So I end up having the per second cancel, because it's the same thing, top and bottom. And now I get meters per wave. Let's take a look at this now. Meters per wave. What is a meter? What's that? What is that a unit of?
Distance.
Distance. And what is a wave? Well, this is a wave. A wave is the picture that is created by having that circle spin around in the first place, right? So now what I have is this thing. We've created a new unit. I don't have a name for it yet, but what it shows me is that if I divide V divided by F, I get this result in meters per wave. Well, that's like the length of a wave. Well, that's kind of a wavelength. Well, that sounds familiar. We actually use the Greek letter lambda for that. And if we divide our velocity, which is how fast our thing is moving sideways, divided by our frequency, we get a wavelength. We actually get a physical carving out of a distance covered by one wave. And it's based on velocity and the frequency. So now what we're going to do is we're going to take that and we're going to try to use it. Okay, so we have our wavelength is equal to V divided by F. Okay, so any musicians in here? What's the frequency of a concert A? Somebody, what's the frequency of a concert
440
A?
hertz.
440. That's very good. Okay.
440 hertz.
Okay. So, what's the speed of sound through the air? It's roughly 330 meters per second. What's the wavelength? 330 divided by 440. Three-quarters of a meter. So when you play a concert A, roughly at sea level, the pressure wave that comes out of it at the speed of sound is about three-quarters of a wavelength long, or sorry, three-quarters of a meter long, which is about 30 inches. So now here's another question. If this is made by a vibrating string or by a wind instrument, which is tuned because it's a hollow tube, if we now have that, and this tube or this string makes a 0.57 meter wavelength that's cast out into space. How do you think we make a higher wavelength, a longer wavelength?
Lower the frequency?
Right. How do you lower the frequency?
Your
A lower note. How do you tune an instrument to make a lower note? If you play a woodwind, for instance.
You lengthen
You
the
extend it. That's right. You make it bigger, you make a lower frequency and a longer wavelength. How do you make it sharper? How do you raise the pitch?
shorter.
Make it
You make
shorter.
it shorter. Okay. Well, this is a perfect analog for how antennas work because they work the exact same way. And we're going to get to that. So now what we have is this great relationship between frequency and wavelength. So V is equal to F divided by, no, F times lambda, or lambda is equal to F divided by V. No. All right, so this is why I'm showing you this. Because, yeah, you know, sometimes it's not so easy to remember all of this. You can, there's only three variables there, but you can still mix them up. And it's not that hard to mix them up. So the way we typically do this is we do a V and then an F and a lambda with this little pie chart. And the way to calculate this is we say, okay, well, we know our V, or we know our F, or we know our lambda. If we know any two of those, so let's say we have our velocity is 330 meters per second. And we have a frequency of 1000 hertz. Okay, so what's the unknown here?
The lambda.
We have the little lambda. Okay, so what we do is we cross that out. And what are we left with?
V over F.
V divided by F, because there's a divisor bar there. This is a very convenient way of not screwing up these little equations. And then we can just divide it, 330 divided by 1000. You have to make sure the units are right. Not too many zeros. There we go. And 330 meters per second divided by 1000 hertz is 0.33 meters. Okay, so we can now take our basic formula and use it in a way that we never forget anything and we can always calculate stuff. But now we're going to say, okay, well, that was sound waves. We're going to add something to this. We're going to change this wave into, let's say, light wave. All right, so we now have a light wave. How fast does light travel through space?
330.
How fast does light travel through space?
3 times 10 to the 8th.
Yeah, 330 a million
300
meters per
million
second.
meters per second. Yes, Ezra. What we're gonna estimate. We're going to go to 300 million because this is an engineering class. All right. So, and in engineering, we round things. So, 3 times 10 to the 8th. We now have, notice, 8 zeros here, so we're going to cover exponents as well a little bit later. If you're not particularly comfortable with exponents because you've either never taken it or you've forgotten them. But now we have 300 million meters per second. So could we write the same thing, V F lambda? Absolutely. Except in this case, what is our V? $300 million meters per second. All right. So we could calculate that. Let's take a look at a frequency of let's say 100 hertz. So we want to know what our wavelength is. We don't know what our wavelength is. We cross this out, and we have our wavelength is equal to 300 million divided by 100. All right. So we just cross out some zeros, and we get 3 million meters, or 3,000 kilometers, or basically the distance from like here to Chicago. Right? That's a pretty long wave, but that's what it is. If we happen to have something traveling at the speed of light at 100 hertz, that is how long the wave actually is. Interestingly, if we look at power, which is 60 hertz, we will find that the wavelength is about 5,000 kilometers, or from here, from the west coast to the east coast. That is one wave. That is one wave. So that wave, if we were to draw it as a wave, would actually be from crest to crest, or for one full period where it repeats itself, that would be 3,000 kilometers long. That's a pretty long wave. We don't usually deal with stuff like that. And in fact, clearly that isn't light at that point, because light waves are much smaller than that. So it's obviously something else. So what we're going to do now is we're going to say, okay, well, let's do something a little more useful here. Let's make our V and our F and our lambda. And V is still the speed of light, because we said we're going to deal with things moving at the speed of light. And we're going to make our frequency here 100 million hertz. Okay, well, this is sounding a little more convenient, isn't it? We're going to say, what's our wavelength here? Cross that out. V over F is equal to 300 million. Somebody has a cat. Divided by 100 million. Sorry. Is 3 meters long. Okay, well, how long is 3 meters? That's about 10 feet. That's also known as 3 meters. Does anybody know what 100 million hertz would be used for? You use it almost every day. If you're in your car.
Is that going to be GPS?
No.
FM radio.
FM radio. Yeah. Okay. Well, so clearly things moving at the speed of light make some pretty long waves because they travel really fast, right? Well, as it turns out, we don't call those waves light waves at that point. They are essentially identical to light waves, but they are not light waves. So what they instead are is a light wave with a very long wave. And what that ends up looking like is, if we were to spread that out, is that it's not really a light wave anymore. It's actually this. And I believe this is actually in your in the packet that I sent out to everybody. And notice that all the way on the right-hand side, we have our colors. And that has some very, very small wavelengths, like 100 nanometers, 1 micrometer. As we go to the left, we get to infrared, and then eventually at some point around 1 millimeter in wavelength, it changes from infrared to microwave. As you go to the left, the waves get longer and longer and longer by a factor of 10 every time. And notice on the top, you have that, for instance, frequency, which is like 300 megahertz, 3 gigahertz, 30 gigahertz. To the left, you have 3 megahertz, 300 kilohertz. Well, what do you notice about this vertical section? 30 megahertz and 10 meters. If you multiply those together, what do you get? 30 times 10.
300.
You get 300. Well, okay, so now let's go back to that thing. And what was the speed that we were dealing with?
Speed of light.
Speed of light. So in fact, we're going to replace that with the letter C because that's the speed of light. And the fact that it's 300, well, that is significant, but also what it means is that we obviously absorbed some zeros there. So the way that we normally, the way we usually do this is to say that instead of doing this, where we have our 300 million and our frequency in hertz and our wavelength in meters, we usually don't deal with stuff that's smaller than a megahertz, which would be a million. Well, there's a factor of a million up here, and we usually deal with megahertz here anyway. So what we're going to do is take those zeros and absorb them. And instead of dealing in hertz, we're going to deal in megahertz. Most of the stuff we deal with is in megahertz anyway, so that makes sense to do it. It makes the calculations a lot simpler.
Gotcha.
So now, this basically now becomes part of the electromagnetic spectrum. The electromagnetic spectrum is this entire band, which goes from zero frequency, infinity wavelength, all the way at the left, which also was called DC. It has no frequency. All the way to the right, which would be infinite frequency and infinitely small wavelength. What is important to note about this is that as you go from left to right and the frequency increases, these energies, all this energy is carried by particles which are massless called photons. They are the same thing that we learn about in physics that carry light. And what happens at the left-hand side is that the photons have very low energy, and at the right-hand side, they have very high energy. Has anyone ever had an X-ray? Probably. Okay, what's a characteristic function? What's a characteristic thing about X-rays?
They can see your bones and see
They can
through your
see,
skin.
they can see right through you. Yeah. Okay, they have a lot of energy, enough energy to pass completely through you and have a picture taken on the other side. As you go through ultraviolet, what can ultraviolet do to you? It can give you a sunburn.
Yep.
Right? And then you go through the different colors, red, orange, yellow, green, blue, indigo, violet. Then you're into infrared. Infrared causes heat. You feel heat. It won't burn you. It'll give you a temperature burn. Ultraviolet will actually like do damage to your cells. That's why ultraviolet exposure can cause skin cancer. what happens is as you go to the left, the energy contained in every photon is lower and lower and lower. Radio waves are no different than light. They are just a different color of light. They are a long wavelength, low frequency, low energy color of light. So it's important to note that they're all part of the same thing. Okay, so now that we've established that and we can use this, so now let's say, okay, well, we have a frequency of 30 megahertz. Okay, so if we have this number 300 and then 30 megahertz, we don't know our wavelength. So our wavelength is equal to 300 divided by 30, which is?
Oh, that's
Which
10.
is 10 meters. Anyone done any studying yet through the book?
A skosh.
Frequency band.
Yes.
Yeah, interesting, isn't it? Well, okay. So we have this tendency to call things by the simplest name possible, right? That makes sense. So in a lot of cases, it is easier to call a band of frequencies on that electromagnetic spectrum by the approximate wavelength of the band. So notice that we have, it's not really 30 megahertz, but we have a band that covers from 28 megahertz up to 29.7 megahertz. That is nominally known as the 10-meter band. Most amateur bands are known by their approximate wavelength in meters because, you know, it's just easier to say 10 meters versus 29 megahertz. Now, we also have another band. Notice this 70 centimeter band. This is one of those rare instances where we call this band nominally 440. So we will sometimes jostle stuff and throw them together. Like a dual band handheld will be a 2 meter and 440 dual band because 440 is easier to say than 70 centimeters. It's shorter. It's just one of those things that, you know, a lot of people do. Yes, it's correct to call it the 70 centimeter band. People do that, but we usually just call it 440. Okay, so before we go any further with that, notice that what we did here is we used frequency in megahertz, right? And again, the reason we do that is because most of the time we're dealing with megahertz, and that also allows us to substitute just the plain old number 300 for the speed of light. This is close enough for every calculation that you'll ever do with regard to this stuff. Now, it is also important to note that how big is this electromagnetic spectrum? I mean, literally, how big is it?
Infinite.
Infinite. Okay. So this electromagnetic spectrum, if we look at how the waves are made, they have an electric part and a magnetic part, and we're going to cover that in a little bit. But these different sections of the spectrum, which are very important to amateur radio, have different names, right? Every section of this spectrum actually has a name. So this down here under the letter A, that's medium frequency. Below that is low frequency, and then there's extra low and or very low and extra low, VLF, ELF. So the ones that you will most likely become involved in are 3 to 30 megahertz. We call that the HF or high frequency band. 30 to 300, which is the VHF or very high frequency band. And the 300 megahertz to 3 gigahertz. Giga is mega means million, giga means billion. So that's the same as 3000 megahertz. We call that the UHF band. Those are just memorization. You have to remember which is which. We use them all the time. The more you're on the air, the more you will become used to it. But for now, you just got to remember it. Now, interestingly, and very importantly, this band from 3 to 30 gigahertz, there are lots of ham bands in there as well. And what's interesting to note about that is that we're going to take a look down here. Between 3 and 30, how much physical space is there between 3 and 30? If you were to subtract one from the other.
That's 27 megahertz.
27. How about between 30 and 300?
Yeah, 270.
270. How about between 300 and 3000?
2,700.
How about between 3,000 and 30,000?
Yeah, 27,000.
27,000. Okay. Up here, 270,000. Up here, 2.7 million megahertz. Do you see a trend here?
Yeah, 2 and 7.
Well, the fact that each one is 10 times bigger than the previous one.
Oh, yeah, yeah.
This is, okay, now, this is really, really important because does anybody use Wi-Fi?
Y'all do.
Raise your hand if you're using Wi-Fi. Okay. Wi-Fi, do we like low bandwidth Wi-Fi or high bandwidth Wi-Fi? Does anyone like streaming?
Oh, yeah.
Everybody likes streaming, right? Data requires bandwidth. The more data you have per second that you want to get across, the more bandwidth it takes. So if you have a signal, a very narrow signal that looks like this, where the frequency is spreading left and right, takes a very small space. A Wi-Fi signal might take this much space. And let's say that we want gigahertz Wi-Fi in our house. Okay. This needs to be, let's say, 1 gigahertz of available space. So now let's go back to our chart here, which did I close it? Oh, that would be stupid. Give me a second here. Okay, so we're going to go back to our chart. And remembering that we needed 1 gigahertz of space. Which band are we going to find 1 gigahertz of available space? Is it going to be between 3 and 30 megahertz? Definitely not. How about between 300 and 30 and 300?
No.
No. 303 gigahertz? Barely. How about up here between 3 gigahertz and 30 gigahertz?
There we got space.
There we go. So what that means is the higher the bandwidth that you want to use, the more physical resource you need to have available, which is why satellite services and things like that, where you want to carry a lot of bandwidth, require these very, 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 very high frequencies. So they become very much coveted at that point because people like their streaming movies. People like their satellite service. People like watching TV and seeing a football game from across the country in real time, right? That is high data rates. That requires a lot of bandwidth in order to send it, which means it requires a very wide frequency spectrum. So there is a frequency chart that is published by the National Telecommunications Information Agency, and it looks like this. You ready for this? Okay, here we go. Has anybody ever seen this?
No. Oh my goodness.
This is a frequency spectrum chart of all the frequency allocations in the United States.
Wow.
These are between 3 and 30 megahertz, 30 and 300, 300 and 3000, and so on and so forth. The same way that we just looked at how those things were laid out. And what do you notice about all the stuff here at these really, really high frequencies?
Pretty crowded.
It's really freaking crowded. But as it turns out, this is actually between, let me make sure I get my cursor back. This is between 30 and 300 gigahertz. That band is actually really big, but notice what most of the stuff up there is used for.
Phones.
Satellite stuff in space.
Satellite, 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 radio astronomy, satellite, 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 satellite. Most of that is, but notice, what do you see interspersed in all of those?
Amateur radio stuff.
Yeah, isn't that cool? Look at that. We have a band available to us between 241 and 250 gigahertz. You want to do your own high for what really, really high bandwidth stuff? That's a ham band. We have all these experimental bands. I mean, sure, we've got all these other amateur bands, which are in the high frequency, which is worldwide communications. And we have all of our VHF stuff. Like right here is the between 144 and 148. That's the 2 meter band. Notice it even says amateur satellite. That's how we talk to the International Space Station. We've got more frequencies. This is that 70 centimeter band or 440 right here. Notice we share it actually. This is another interesting thing. We share it with radio location. This is ISM and military stuff. So that's actually a shared allocation. We have another shared allocation between 1240 and 1300. And here's another really weird one. Between 2390 and 2417, and then up to 2450. Does anyone know what that is right adjacent to? Anyone recognize those frequencies? Anyone have 2.4 gigahertz Wi-Fi?
That'd be Wi-Fi and your
That'd be
microwave oven.
Wi-Fi, and your microwave oven is 2350. Yeah. So we are adjacent to, and in some cases, sharing frequencies with Wi-Fi. What is our frequency? What is our power limit available to us from that first one of those first things we talked about? Anybody
1500
remember?
watts.
1500 watts. What is a Wi-Fi router allowed to transmit? How much power? About a half a watt. And it can use the antenna that is specified for that particular thing. What if we wanted to take that Wi-Fi router and put it through an amplifier and hook it up to a dish antenna? Legal?
Yeah.
Yeah. We actually do it all the time. It's actually called ARDN, AREDN, which is the Amateur Radio Emergency Data Network. We have a whole bunch of mesh things. If anyone does mesh technology, we do something called ARDN, which is a mesh technology. And let me share that. And as part of that mesh technology, look at that. We have 2.4 gigahertz and shared with unlicensed, except that we can run massive amounts of power and hook it up to any antenna we want. Then we can take it and we can stick it on a mountaintop and we can cover distances of 30 miles essentially using Wi-Fi.
At any point, does that become dangerous then?
It can. That's why, we also go through RF exposure calculations as a requirement of putting a station together. And we have safe zones and unsafe zones. Essentially, we have places where nobody should go, places where only knowledgeable people should go, and places where the public is allowed to go. And those are all different distances. And different frequencies affect the human body in different ways. So we have access to lots of them. So it's important for us to, again, understand, which is why there's this thing called this class, why we do it in the first place. Everybody ready for a 5-minute break?
Yeah, right. I can use some coffee.
All right, back in 5 minutes, y'all.
Book for us to read and test the same questions, but it's not teaching the questions. The assignment is totally different. It's very technical. It's right up your lower line, it's right there. Oh, Lord. What's your good stories? Date on. Date on.
Hello, everyone.
Thought I was going to be over 100 people. I really thought today was a day I was going to be over. I even expanded the classroom to 500 people.
How often do you give these classes?
When time permits.
Okay.
It's I do it because I like to, and I also still have a full-time job and kids, and I have I'm the section manager for the American Radio Relay League for the state of Oregon. And I do other volunteer stuff, like a lot of other volunteer stuff. I work with several schools and things like that. So I try to squeeze things in when I can. It's usually come down to being able to do it when I'm on a 3-day weekend or something. That way I don't feel like I did my entire weekend. Because
Yeah.
by the time the weekend's over, I'm pretty beat. So yeah, 12 hours of doing this. 12 hours is a lot. So, and you know what? I'm still getting people asking me if they can come. It's like, sure. Yeah, why not? Talk about waiting for the last minute. Yeah, more power to it. All right, everybody ready to go? Everybody back? Everybody awake? I hope.
Oh yeah, just make up a pot of coffee. I'll be ready in a second.
You made enough for everyone, right?
Come and get it.
Well, like I said, I sent in one of my notes. I once did try to pour coffee into the microphone, give it to everyone, and it didn't work. So
Just for a bit.
yeah, sound goes through, but coffee not so much. So there was also that time I had donuts and I just tried to stuff a donut into the mic, and that didn't work either.
Well, they did that in Willy Wonka. They were able to.
Well, exactly. If Willy Wonka could do it, why can't we? Okay. It was called Wonka Vision, if I remember correctly. He sent a chocolate bar, but it became miniaturized. Poor Mike TV. Okay, so let's see. No nonsense study guide. Now it's a good time to mention the no nonsense study guide, which I hope everybody has a copy of. So it looks like this. Does everybody have this or has seen it at least? It's a free download. I included it in the download. If you don't like the download that I sent you, there's a download available. Does everybody have it, I hope? There's a download available right from the guy's website for free. You could also have bought a paper copy for those of you who like having paper copies to take notes on and stuff. And the reason I like this book is because it focuses on the things that are correct. And it covers all the questions with a little bit of, literally, it covers all the questions with a little bit of explanation. Sometimes a little more than not, sometimes a little bit less, but it basically covers everything. And the price is right. So notice this radio wave characteristics. This is where we are right now. We've basically just discussed, we just spent the last hour discussing what it is that waves are and what it is that they do, and what the frequencies and wavelengths are for radio waves and stuff like that. Okay, everyone would agree that we now know that radio waves travel at roughly the speed of light, speed of light. Okay, so what we're going to do now is we're going to stop sharing that and go back to here. And we're going to share a whiteboard. There we go. All right. So we're going to discuss the fact that the electromagnetic spectrum is called the electromagnetic spectrum and why. So what we have here is we're going to draw three-dimensional axes. We're going to have the x-axis and the y-axis and the z-axis, unless you're in Canada, in which case it's the z-axis. So we have our x, y, and z axes. Now, it is important to note that the way I've drawn these in kind of like an isometric form is that these are all perpendicular to each other. The intent is that they are all perpendicular to each other. So the x and y axes are perpendicular. The x and z axes are perpendicular to each other. And the y and z axes are perpendicular to each other. So what we now have is a three-dimensional space. And what we can do with this is that we can say that there is this wave that's going to be traveling. And I'm going to choose a different color, I hope. Okay, so we're going to make, in the x-axis, we're going to make a wave that looks like this. So notice it's traveling, it's advancing along the z-axis, and it's laying flat on the x-axis. At the same time that that is happening, we're going to draw a wave that is perpendicular to that. So it's going to have the same crossing points, except that it's going to be going up and down. And notice that they have the exact same frequency. They have the exact same wavelength. Electromagnetic waves have two parts. They have an electric portion and they have a magnetic portion. These are going to be proportional in size to each other, in amplitude, based on the space that they are traveling through. The energy, the direction of travel of energy is from the left to the right. Okay, so these vectors, because a vector is a direction and an amplitude, this is known as the E vector. This one is known as either the B or the H vector. Those are magnetic fields. And this one over here is the S vector. What's important to note is that if you take your right hand, and it must be your right hand, it cannot be the left hand, you have three fingers, your first three fingers. You have your thumb, your index finger, and your middle finger. And if you stick them out, you will notice that those make a perpendicular set of axes. If you hold your fingers up, your thumb is first, your index finger is second, and your middle finger comes out third. This is the right hand rule, and you notice that if you look at how I drew those, if the electric field is on your thumb and the magnetic field is on your index finger, then the direction of travel of energy is on your middle finger. This is the right hand rule. This is also known as a cross product, which we do in calculus. So what this basically means is that the way that the electric field and the magnetic field per Maxwell, if anyone's ever heard of James Clerk Maxwell, who wrote down Maxwell's equations, which defined electromagnetic radiation in a formalized fashion, what he did was to figure out that the electric field and the magnetic field are always perpendicular to each other. Electric field and magnetic field are always perpendicular to each other, and they are perpendicular to the direction of travel of the wave. So if you want to think of it this way, as energy travels to the right, and the carrier for light energy is a photon. So as the photon travels to the right, it creates a disturbance in space, which is an electric field and a magnetic field simultaneously. And again, those are proportional to each other, defined by Maxwell's equations. What's important to note here is that the electric field, the direction of the electric field defines what's known as the polarization of the wave. The electric field defines the polarization of the wave. So if you have a wave where the electric field is going back and forth parallel to the Earth, we think of that as horizontal. That would be known as horizontal polarization. If the field is going up and down perpendicular to the surface of the Earth, we call that vertical polarization. And the reason this is important is because the orientation of a piece of wire has a lot in determining which direction the electric field is oriented. All right, so now we're going to get into a little bit of electrical stuff. So you're like, okay, well, what actually makes this stuff happen? Right? So we have these waves, they exist, they travel through space. Well, none of this would be possible without this little dot, which is a fundamental particle called an electron. None of it would be possible without this little electron, which has a little letter E with a negative charge. And that is a fundamental particle. You cannot break it down any further than that, so far as we know. When you take this little negatively charged particle and move it through space, it creates a magnetic field. And it turns out that the magnetic field makes a path around its direction of travel. As an electron sits there in space, it has a negative charge. Here's the dot, the negative charge. Around it is an electric field. Far away from that electron, the voltage that you get is 0 volts. at the point of the electron is the center of the charge. You actually have a gradient, which is like a change in the amount of electricity that you're basically feeling at any given point. What happens is now, if you move an electron, that will change. Well, it turns out that in addition to making a magnetic field, which then makes like a loop around the line, this actually causes disturbances in the electric field around it if we were to move that charge to the side. So basically, when you move an electron, you get a changing electric field and a changing magnetic field. Those then propagate at the speed of light out into space. This is the basis for electromagnetic waves or electromagnetic radiation. And radio waves are just a different color of light of electromagnetic radiation. So, how do we make radio waves? What do? We take an electron and
you move it.
Accelerate it.
move it. You move it. Yeah, you just move it. You take an electron and you move it. When you move an electron, it makes radio waves. It sends out energy in the form of radio waves.
That's
So
all
in order to make any of this work, now we have to find some way to move electrons. All right, so now we get into Ohm's law. Okay. Does anyone know Ohm's law?
No.
E equals IR.
E equals I times R. Okay. So we have to move electrons to make things happen, right? That's basic radio 101. That's how you make radio waves. Now, it is hard for us to just take an electron and move it. We don't normally just look around and find electrons just sitting there on the table, right? You can't just like physically pick up an electron. Electrons are really tiny. They have an incredibly small charge, but fortunately they're very, very small, and they're actually found on the atomic scale, which means that if we were to look at, let's say, an atom of copper, which has 29 protons in its nucleus and 29 electrons flying around in the shells outside of the nucleus, well, copper is kind of a special thing. Copper's got a lot of electrons. It's not that uncommon in the universe, or at least on Earth. And what's nice about copper is that those electrons that are kind of far away from the nucleus at the center aren't really bound all that tightly. So if we can do something like take an electron, if we can manipulate an electron and shove it into a copper atom, what we get is another copper atom coming out the other side. What's our net effect? We now have electrons moving. Okay, if we have electrons moving, what can we do with that?
Make a frequency.
We can make energy. Wow, okay, we can make electric and magnetic waves, electric and magnetic energy coming out of that. Okay, well, we're getting close now. So now what we're going to do is we're going to take that copper atom and we're going to hook it up with another one and another one and another one and another one and another one. We're going to take them and form them into a big long line. Okay, so what do we call a big long line of copper atoms that we find in the world every day?
Wire.
It's a piece of wire. Yeah, copper wire. Okay. So now what we can do is if we can take an electron and shove it into this wire and give that electron some other place to go, like maybe back to the source, we can have a continuous chain of electrons moving through that wire, which means we can make electric and magnetic fields out of that. Okay, well, that's pretty cool, right? But now we have to find something that can move and essentially force those electrons to move through that copper wire. So we have figured out that if we were to take two dissimilar metals, form them into something called a battery, we can create a positive terminal and a negative terminal, and it turns out the electrons come out this side, not out of the other side. The electrons come out of this side. If we complete this loop, electrons flow this way, through here, through here, through here, and then back to where they started on the other side of the battery. When we charge up a battery, that's basically providing an ability to push electrons out of the battery and through a circuit. Well,
I'm sorry, batteries take the electrons back in through the positive side and out through the negative?
yeah. Well, think about it. What charge are electrons? They're negative. Okay, now we're gonna get to the mistake that was made, right? So a battery is really a source of electrons, and then they come back to the other side. But by that point, it's the chemical reaction is such that it's either reversible or not. You've either used it up or you need to recharge the battery. So we are trying to force electrons into this circuit. We're trying to move electrons. We're trying to make them move. This is known as electromotive, which means moving, force. That is the battery's ability to move stuff. It has an electromotive force, which is known as an EMF, or we call it a voltage. So the ability to move electrons is a voltage. That is the voltage of the battery. That's the voltage of the source. We measure this in the units of volts, named after volta. We use the big letter V or the big letter E to indicate electromotive force. When we go to our Ohm's law, we have E equals I times R. Well, there's the E. Okay, so we just determined what E was. E is the electromotive force that pushes stuff. Electromotive force. Electro, electrons, motive, moving, and force, the ability to shove stuff. Okay, so now, electromotive force causes what? It causes something to move. What moves?
Electrons.
Electrons. Okay. Now, we know that electrons are very, 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 very small. So we know that since electrons are very, very, very small, it must take an awful lot of them to do anything because they're really, really tiny. But fortunately, they're really tiny, and we actually can move an awful lot of them. Okay, so we now have electrons moving through here. And what we have is a blob. We have this unit called a coulomb, which is a number of electrons. It's a very, very large number of electrons. Lots and lots of electrons, like 10 to the 19th power. Huge number. Well, if we can move 1 coulomb of electrons, 1 coulomb worth of electrons per second through something, that has a name. This is a current, which is a letter I, and we measure those units in amps, named after ampere, and we use the letter A. So this is 1 amp is a 1 coulomb per second current. It's a lot of electrons. But again, they're really tiny, so we usually just ignore that fact. And we just say we have 1 ampere of current. That's the number of electrons moving past any point per second. Okay, so now what we can look at this point is that, okay, we have our current flowing, which is being pushed by our electromotive force, which is our voltage. And now we look at what it's flowing through. This stuff right here. Copper is very special because copper has a lot of electrons that are very, very loosely bound, which means that if you push one in, another one will pop out the other side very, very easily. There are other atoms, for instance, if we have, here's our nucleus, and here's our electrons floating around, where they are very tightly bound, and you can try with all your might to push an electron in, and it will not be accepted, and you won't get anything out the other side. We call these conductors, and we call these insulators. So if we were to take that copper wire and replace that with, let's say, air. Air is mostly nitrogen and oxygen. It takes a lot of voltage to make a current flow through the air. No, 100 milliamps will kill you, by the way. 10 amps will definitely kill you. Okay, so insulators don't like to carry current very well. Conductors do like to carry current very well. So let's talk about what are some conductors other than copper? Everyone?
Gold.
Gold is great.
Aluminum.
Aluminum is great. The only problem with aluminum is that
it's hot.
It doesn't actually. The only problem with aluminum is that it oxidizes very quickly on the surface. Silver's great.
Water.
Yep. What was that one?
Water.
Oh, that's a great one, but we have to give it a qualified yes. Water. Water, deionized water is a very poor conductor. Salt water, as somebody noted, is great. Deionized water is just H2O, and it does not conduct electricity well. As soon as you put salt in it, it conducts electricity extremely well. Okay, so what are we made out of? Not 70% of our bodies.
Salt water.
We are 70% salt water. So that is why you can be killed quite easily by a very low current, because it doesn't take much to going through your heart. It doesn't take much current to disrupt the electrical signals that cause your heart to beat. And we happen to be made of salt water. All right, let's see. How about how about some insulators?
Lead.
Insulators? No, lead's actually a decent conductor. It's just,
Rubber.
we use it for we use lead for solder. If it weren't a good conductor, we wouldn't do that. Yeah, glass, silicon. Silicon can be. Plastics, ceramic, some ceramics.
Yeah, rubber.
Rubber. How about air?
Yep.
Has anyone ever been near the ocean?
Yeah.
Has anyone ever heard a power line near the ocean? I have.
Yeah.
Oh, yeah.
Salt air.
Because there's salt in the air. Yeah. Yeah. Okay, so insulators do not like to carry current. Conductors carry current very well. So now what we're going to do is we're going to erase this and draw our circuit. And now we're going to fix that problem. Okay, here's the battery. Current is the flow of electrons. We have established that. However, when it was first devised what current would be, electrons weren't really known to be the carrier at that point. So this is the positive terminal of the battery, and this is the negative terminal. This is the thing that is going to be carrying our current. For the sake of argument, I put in here that this is a resistor. Doesn't necessarily have to be a good resistor or a bad resistor. I just put it in as the current carrying element. So in actuality, the current is the flow of electrons, but by convention, current flows out of the positive terminal. This was one of the hardest things to accept as an engineering student in electrical engineering. The fact that we know that current is actually caused by the current flow, by the flow of electrons going this way, but by definition, current is backwards. They got it wrong. It turns out that it actually makes sense to think of it coming out of the positive, because we as a species think of positive as higher than negative, which is lower, and things flow from high to low, right? So in reality, it's wrong. In practice, we ignore that fact and just get on with our lives. So here's our E, and here's our I, and here's our resistor. Our resistor is something that is made of something that, why do we continue to use conventional flow? Because everybody knows it. No, because everybody knows it. It's just who we are. It's a mistake that was made. It was 180 years ago. You know, we've been living with that and teaching it that way for a long time.
Hey, Scott, is that
Yeah.
related to the notion that lightning actually goes from the ground up to the cloud? Is that
I'm
kind
not
of
sure.
related?
I'm not sure. I mean, it depends where the negative charges are made and what becomes positive. So, but essentially, it's just a connection between 2 points that are at different potential, different voltages. Okay, so a resistor is something that resists the flow of electrons, resists the flow of current. This is measured in ohms. We use the Greek letter omega for it, named after Georg Simon Ohm, who did a lot of work. And so we measure our resistance in ohms. Now, this is specifically with respect to resistance, which is known as the ability of an object to resist the flow of electrons at direct current. Direct current simply means that it's flowing in the same direction all the time. We will cover why that means that in just a minute. So that's our DC current. And these are related by Ohm's law. E is equal to I times R. For convenience sake, we draw that circle again, EIR, like that. And that way you don't have to remember. You don't have to remember if you're trying to say E is equal to, you just basically say, okay, if I don't know my R, then R is equal to E divided by I, because there's a divisor bar there. It's just a convenient way of doing it. So some basic calculations from Ohm's law. For instance, we're going to say that we have this resistor, and our resistance is going to be, let's say, 3 ohms, and we're going to have a voltage of 30 volts. We're going to make a nice simple math problem. Okay, so we do our EIR thing. And which is the one we don't know? That would be our I. So I is equal to E divided by R, which is 30 volts per 3 ohms. A volt divided by an ohm is an amp, so that's 10 amps. That's the current flow. All right, so what we've now done is we have a linear relationship between volts, ohms, and amps. This is the basis for Ohm's law. And I like to point out that we're working in the job that I do, which is building machinery and fixing problems and things like that. 90% of all the problems that you see in a circuit are caused by Ohm's law, or are solved by Ohm's law, or are an application of Ohm's law. The very simple is E equals I times R. 90% of the problems that are caused. If you have a loose plug that's not plugged into a socket properly, what's the problem?
The electrons aren't passing.
Because
much resistance.
Because you have too much resistance, because it's not a completed circuit. It's Ohm's law. 90% of things are related to Ohm's law. 90% of solutions to problems are a function of Ohm's law.
Can I ask a practical question, a practical example here?
You're a little bit you're a little bit muffled.
Sorry.
Go ahead.
Sorry, I was trying to use my headphones. I'm sorry. 1 second. No, I'm
Hey,
sorry.
can hear you fine now.
So, right, yeah, sorry. Thank you for my cat. He's a good boy. I was asking for like a practical, maybe like hypothetical thing. I'm thinking of like the AA batteries, and you put them into a keyboard or something like that. What's the point of that little spring versus on the positive versus nothing on the negative? Is that some sort of a resistor too?
No, it just gives people a reference point.
That's all. Okay.
Yep. And a DC battery is 1.5 volts.
Okay.
A AA battery or a AAA or a D cell or a C cell, they're all 1.5 volts.
Okay.
And why are they 1.5 volts?
Because we make contact with them pretty regularly. They got to stay. Nope. Nothing about safety. Alkaline.
Internally,
that's the way the chemical works out.
The way a battery is a chemical energy storage system. The chemistry of an alkaline battery with the anode and the cathode materials produces a cell voltage of 1.5 volts. Fully charged, it's about 1.65. Okay, so why is a lithium battery what it is? What's a lithium how many volts is a lithium battery?
Flip over my laptop and take a look really quick.
Yeah, but like a single cell lithium battery.
Was it like 1.4 volts?
3 volts?
Oh,
3.7. So that's a rechargeable lithium, like a lithium polymer battery. And it is defined by the chemistry inside. It turns out that lithium is a very electronegative material. Or is that right? No, it has a very high potential. So when you use lithium, you get a very high potential in your battery, just because of the fact that lithium is a very electropositive material. Other metals might not be so good. Turns out that a lithium metal battery, anyone ever seen one of these? It looks like this.
Some of the new solar storage batteries, the lithium iron sulfate.
Like the 3032?
Yeah, this is a coin cell. This is 3 volts. That's a non-rechargeable thing. That's a lithium metal battery, and it has a cell voltage of 3 volts. There's other ones that are like a silver battery that are used for hearing aids and things like that. And they all have different voltages based on the chemistry inside. The difference between a lithium ion battery and a lithium metal battery, they're both lithium. And there's also something called a lithium iron phosphate. The differences between those, this is about a 3.4 volts. This is about 3.7. This is 3 volts. Notice they're all fairly high voltage because they use lithium, and lithium again is a very potentially high voltage metal. This lithium ion is a rechargeable battery. Lithium iron phosphate is a rechargeable battery. This is not. However, the way that these are made, they're used for a very long life. This could be good for 10 years at very low current draw. So, battery chemistry, really important. Okay. So as we move on, we're going to cover this next part, which is what happens when you do this. Okay, so here's my voltage, and here's my current, and then I have two resistors. So what happens to this voltage? If I were to measure this voltage, and let's say this is 12 volts. 12 volts is actually is what we use in our cars, a lead battery, which is actually lead sulfate. So that's why we use sulfuric acid and lead in our car batteries. What happens with this is that one cell is about 2.3 volts. Multiply that by 6, we get 13.8, which is a fully charged lead acid battery. We nominally call that 12 volts. So that's a 6-cell lead acid battery. Whether it's a gel cell or anything like that, it's still about the same. So we nominally call that a 12-volt system. And most of our car batteries and things like that, most of our power supplies are 12-volt power supplies for that reason. Okay, so let's say we have a 12-volt battery, and we measure the difference between the bottom, which we're going to do this with. That puts it at 0 volts. This is also known as ground. That's our reference point for 0. This is going to be at plus 12 volts. How much are we going to get right here?
12 volts.
12 volts. How about right over here?
12 volts.
12 volts. How about if we extended this over to here and
12
connected
volts.
it to nothing?
Wait, nothing.
Yeah.
0.
12 volts.
Really?
Yeah. We have.
It doesn't try to complete the circuit?
Doesn't need to.
Huh.
This whole thing is at 12 volts. There's no current going through it directly. So, I mean, I could extend this all the way out here. There's nothing to consume energy right there. So it's, that's and that's actually called a bus. That's our positive bus, and this is our negative bus.
If there were no resistors there, but we still completed the circuit, coming down.
Well, then you get a short circuit.
What do you mean?
What if I did this?
No, before the resistor. Before the resistors.
What if I just put a short here?
Yeah, and then
then all the current would flow through here.
Right, and that would complete the circuit, and then it wouldn't continue down that line at all. The rest of it wouldn't be hot.
No, you still would.
Okay.
You'd still see, but you'd probably see 0 volts because you'd be pulling all the current through here, and you'd destroy your. Yeah.
Something's gonna be smoking.
Yeah, something's going to be very hot very fast when you do that. Okay, so what we have here is a parallel circuit. Current always flows through the path of least resistance. So let's say I have resistor 1, which is 1 ohm, and resistor 2, which is 1,000,000 ohms. Which way is most of the current going to flow?
Through the 1,000,000 ohms? Isn't it? No?
Go to R1.
E equals
the path
IR.
of least resistance.
Path of least resistance. E equals I times R. We can go through and calculate what it's going to be because this has its current and this has current and they separate. So let's do that. EIR. Okay, so let's look at it for the first one. Over on the left-hand side, I is equal to E divided by R, which is 12 divided by 1, which is 12 amps. For the second one, I is equal to E divided by R, which is 12 divided by 1,000,000, which is 0.00012 amps. Current flows the path of
least resistance.
Least resistance, okay. And now, as it turns out, your current, those add together if you're looking at how much current is actually being delivered here.
Okay.
And if we were to try to figure out exactly what that combination of resistors looks like, there's a formula for that. So I'm going to draw my parallel circuit again. Here's my battery.
Good question.
Yep.
R2, would that even pull any energy?
Sure.
Since R1, it was the easiest path.
What if they were 3 ohms and 3 ohms?
That'd be equal.
They'd be equal. Okay. So the equivalent resistance for this would be R is equal to R1 times R2 over R1 plus R2. And the derivation for this is actually covered in the general class.
Because there's still 12 volts being fed to the input of the resistor.
Yep.
It would still do it. All right.
Yep.
That got lost there for a second.
So in parallel, what happens is that each of the resistors pulls some of the current. So if you were to try to replace this, let's say it wasn't really important that you had 2 of them, you wanted to replace them with 1, you could actually figure out what the resistance, the equivalent resistance is. So this would be 3 times 3 divided by 3 plus 3 is equal to 9 divided by 6 is equal to 1.5 ohms, which is, as it turns out, exactly half of either of those. So who thought that 3 plus 3 is equal to 1.5? Because they're not adding. It doesn't work that way. Now, where they do add, this is known as a parallel circuit. That formula does not work. And that's because the current goes down both paths. It makes the equivalent resistance look smaller. I can draw another circuit that looks like this. This is known as a series circuit. And if you think of it this way, you have our voltage, let's say 12 volts, and the current right here. And it's the same current that has to go all the way through the circuit. So that same current has to experience both resistors in order to get back to where it started, to get back to the battery. So what ends up happening here is that R is equal to R1 plus R2. And in that case, they really do add together. So if I have 3 ohms here and 3 ohms here, those really do add to being 6 ohms. And to the question of what happens if I measure the voltage at different points, every time I go through a resistor, my voltages get lower. This actually has a really profound impact. The profound impact is, let's say that if I were to draw this, and then I had a big open space and another resistor. But I don't know what just happened. There we go. That's weird. I think I can erase that. There we go. What would happen if I had this big open space here?
I mean, the electricity. If it's in a vacuum, if it's on paper, the electricity.
What would happen what would happen if I try to push a current through a big open space?
No flow.
A spark.
This is well, if the voltage was high enough, but let's say
It
this
would
was
jump, but zero.
Let's say this was infinity resistance.
Well, it'd be an open circuit, right?
That's an open circuit. Yeah. How much current goes through? Nothing.
Zero.
Zero. Okay, so if that's the case, my current is 0. And what if each of these resistors is a light bulb?
Nothing happened.
We get nothing happening. This is exactly what happens. Has anyone ever seen Christmas tree lights?
Mm-hmm.
If you get one light that goes out, your whole strip goes out.
Yeah.
Because you get this, an open circuit like that, and then you get absolutely no current going through. And since this is the next part, P, power, is equal to I times E. So there's E equals I times R, and P is equal to I times E, which is the power part of Ohm's law. This is measured in watts. Watts is energy per unit time. That's what makes things light up. That's what makes things get hot, stuff like that. If you have no current, then you have no wattage. If you have no wattage, you have no power, you have no energy, and the lights don't light up. And that's why if you have a blown out light bulb in a Christmas tree, in a string of Christmas tree lights, the whole strip goes out.
So there's a resistor built into those little light bulbs then?
No, the resistor is the light bulb is the resistor.
Oh.
It provides a path. I mean, essentially a light bulb is a classic light bulb
Is a form of
is a
resistance.
resistor. That is what a light bulb is. And by Ohm's law, P is equal to I times E, and E is equal to I times R. This is a resistor. So you have a voltage and a current. If you have a voltage and a current, you can plug them into the power equation and you get power. And the power comes out as light and heat, which makes a light bulb turn on. That is what a light bulb does.
Okay.
I mean, that's the definition of a light bulb. A light bulb is actually usually a tungsten filament. It's just a really thin wire in a vacuum that looks like this.
Okay.
So if that gets, what happens is that carries current and its resistance is fairly high. So when it does that, E is equal to I times R, and then P is equal to I times E. What happens is that you get a voltage and a current that flows through this resistor. That voltage and current create power, and it has to dissipate that power somehow. Tungsten, which is the big letter W, it turns out has a melting temperature which is insanely high, which means that you can get it really, really, really hot before it melts. And because of the black body radiation formula, you can turn it white hot and it still doesn't melt.
Huh.
And that's why light bulbs light up. But if you were to take this element and replace it, come on. If you were to take that element and replace it with an element that looked like this, because it blew out, you would now have an open circuit. It would carry no current. You get no power, and everything else stops working.
Okay.
Aerial spotlights use tungsten rods because of how they burn so bright.
Actually, your standard incandescent light bulb is tungsten.
Mm-hmm.
So a resistor isn't necessarily. I'm sorry. I'm just trying to understand the concept. The resistor isn't necessarily like something you put into a circuit or something that is added. It's just.
It's any type of load.
Anything that carries current. Like, how about this piece of wire?
It's a form of resistance.
There's resistance just there.
There's resistance in the wire. Everything has resistance.
Okay.
It's just a question of how much.
So it's just how much slower we make the electrons move.
It's how much the material resists the flow.
Gotcha.
I mean, they're going to move at, whatever speed they move, but yeah. So but that's why. Okay, so let's take a look at this. So let's say that the resistance is equal to 0.1 ohms in the resistor. Right? This is actually this is a really good thing to talk about, because let's say that this is I don't know, 100 ohm resistor. And you have a resistance of 0.1 ohms. And we have a battery that is 12 volts. So we have a plus and a minus. What is our sum of our resistances? They add together. 100.1 ohms. Because they're in series. They add together.
Right. Okay.
Right? So it's 100.1 ohms. So you know what? For the sake of argument, let's make this 99.9.
Okay.
So now it's 100 ohms total. Okay, so now we have a current flow which goes through both things. It's the exact same current. It has to be, because it has to go through both things to get there. It's like, if you think of a series, it's like, you're watching a TV series, you have to watch every episode. Current has to go through every resistor. It's a series. You can't watch a TV show in parallel and know if it's a series, you're going to miss stuff, right? They're not parallel episodes where you could just watch one and, it doesn't, and it has nothing to do with any other.
Yeah,
Okay,
yeah.
so let's say that we have our 100 ohms of resistance, and for the sake of argument, let's make this easy. Let's make this 10 volts.
Oh, it's just an anime.
Because I can do that. It's math, right? Okay, E equals I times R. I is equal to E over R is equal to 10 divided by 100, which is equal to 0.1 amps. So my current is 0.1 amps. How much current is going through every point in that circuit? 0.1 amps. You can't have, there's no accumulation of electrons anywhere, so it just goes through everything. 0.1 amps, 0.1 amps. Okay, so could I figure out, if I know that this resistor is 0.1 ohms and the current is 0.1 amps, could I figure out what the voltage is there if I were to measure the voltage across it?
I'm sure you could.
Well, how would you do it? What law would you use?
That Ohm's law then.
Ohm's law. E is equal
Just
to
run it backwards.
E equals I times R. Okay, which is, what's my current? 0.1 amps. And what's my resistance? 0.1 ohms is equal to 0.01 volts. So if I tried to measure my voltage here, I would see 0.01 volts. Well, I think in that case, I would probably have 9.99 volts left. I could go through the math and prove that, but I think what's cool about that is that, well, I used up 100th of a volt here, and I have 9.99 volts over here. All right.
So you're using okay.
You're basically, some of your voltage gets lost, and yes, that's a forward voltage drop. That's a voltage drop. So the next thing that happens here is that we can figure out, since we now know that we get 0.1 volts, we're going to change color because we're going to change to 0.1 volts, 0.1 amps. Can we figure out how much power gets consumed in that? Sure. What's Ohm's law? What's the other part of Ohm's law? P equals I times E. Okay, well, P is I times E, and our I is 0.1 amps, and our voltage, 0.01 volts, is equal to 0.001 watts, or 1 milliwatt. All right, how much of that power, what happens to that power that gets burned up in this resistor section? What does it turn into?
Heat.
Yep, power is turned into, power that isn't used for other things is turned into heat. Okay, well, that looks pretty good, actually. Only 1 milliwatt? That's great. Which means that the rest of the power being delivered can actually go to this thing called the load, which is what we want to use the power. All right, so now let's look at this, and instead we'll take this circuit and we will say that, in fact, this wire is starting to go bad. And it's not 0.1 ohms anymore. And when I say go bad, it's starting to degrade, and let's say that it's now 2 ohms. Well, unfortunately, that also means we have to redo all the calculations in the circuit. But this is the kind of stuff that we have to do because this is what solves problems. And since we already have some experience doing all that, we can do that. We can't say that that's true anymore. And for the sake of argument, we can make this 98 ohms. So that we still have 100 ohms. And that current's not right anymore. Actually, the current is right. So we have 100 ohms. So we still have 0.1 amps. Okay, but now if we were to try to measure our voltage across this thing, which is what the wire is now doing, what law do we use?
I'm sorry?
What law do we use to measure the voltage?
It's still Ohm's law, right?
Ohm's law again. Yeah,
Yeah.
okay. Is equal to 0.1 times 2 is now 0.2 volts. Well, okay, we started off with 10 volts in the first place, and we just wasted 0.2 volts. So how much is left by the time we get to our load?
Okay, gotcha. So then it'll be 9.8.
9.8 volts.
Okay.
Okay, so as our resistance in our wire starts to go up, what do we start to do? We start to lose available voltage for the thing that we actually need to run. And what's our power that's consumed in that first resistor now? What's our law? What's our calculation? P is equal to
E times I.
Yep, or pi, P equals I times E.
Oh, there we go.
Is equal to 0.1 times 0.2 is equal to now 0.02 watts. So it doesn't seem like much, but that's now 20 times bigger than it used to be. Because before it was 0.001 watts.
Yeah.
So the problem here is that as your currents get bigger and your resistances get smaller, your voltage drop and your power loss goes up, 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 up. If that is a wire inside your wall, what will happen to you?
I mean,
your house will be on
Your
fire.
house will burn down. That's right. Your house will catch fire, right? Because this is inside your wall. So we add a device right here, which is called a fuse, which senses how much current is passing through a particular circuit and can hopefully prevent your house from burning down if it goes too high. The other thing, though, that can happen is that if, in fact, you do have a piece of wire that is going bad, all the fuses in the world will not help you because you're not actually pulling too much current. You're just having wire that's getting too hot. This actually happened in the 1970s. Does anybody remember this? Anyone old enough to remember this happening?
We don't use aluminum wire anymore.
That's right. Well, no, you can. We do. What's the problem with aluminum wire?
Well, it
Not
corrodes.
as
Oxidizes.
conductive as copper.
It is conductive,
but it
but
corrodes in the air.
Oxidizes.
it oxidizes in the air. So if you have a connection between a wire and another aluminum wire and you like put them under a wire nut, unless you bathe them in like grease, they will oxidize and then you'll get a high resistance. If you get a high resistance, you get a lot of power, you get a lot of voltage loss. If you get a lot of voltage loss, you get a lot of power dissipated. And what happens is that these wires at that junction become very, very hot and they burn your house down. That happened a lot in New Jersey in the 1970s because they used aluminum wire because it was cheap. And they didn't quite understand how to protect it from oxidation.
Should have taken a ham radio class.
Well, 90% of problems are Ohm's law. They really are. Okay, so now we're going to get back to something else, which is, okay, so we're going to get to this, which is a battery. Which direction does current come out of the battery?
from the negative.
It does, but we're going to say that the current
we
comes
don't
out of the
care.
plus. Right. Okay, so the current comes out of the positive, and it goes around like this, makes a loop. Okay, so there's our current coming out of the positive, goes back into the negative, and we have this thing which is our 0-volt reference, which is known as a ground. We call it ground because it's our reference potential. We consider the Earth, which may or may not actually be 0 volts in the cosmic scheme of things, but we call that our 0-volt reference. So that's our ground. Okay, so once we have that, we can say, okay, the current is always flowing in one direction. This is known as DC, or direct current, always going in the same direction. The other thing that we can do with this, if we really decide that we want to, is take this battery and we can throw a switch on it and have somebody there with very, very fast hands taking the battery, pulling it out, and doing that with it. When they do that, what's going to happen to the current?
Alternating current.
It changes direction. It now comes out of the plus and it goes this way.
Oh, that's what that means. Oh, duh.
That's not AC anymore. That's not DC anymore. That's AC. If we switch it back and forth and back and forth. So if that is the case, and we no longer have current only flowing in one direction, now it's flowing in one direction and then the other direction, and we change this at a certain frequency, we have a frequency of our wave. Well, we could, if we were to plot our voltage, go like this. Where we have our plus and our minus. And if we connect the dots, that actually forms something called a square wave. Well, it turns out that most voltages don't look like that. And that's at least not in the analog world. That's what we might have in digital electronic circuits. Power supplies don't typically do that. And it turns out that if you go through something called a Fourier analysis, and let's say you have this switching at a frequency of 1,000 hertz, that makes all kinds of electrical noise. So we typically don't do stuff like that. Besides the fact that we want to be able to make power, we actually want to be able to make it at a given frequency, and we want to be able to make it easily and in large volumes. So what we do is we take electric motors, and we use 3-phase electric motors, or sometimes even more, and we spin them inside a magnetic field, and they generate a voltage that looks like this. As I struggle to erase that. They make a voltage that looks like this.
Hey, we recognize that.
And what's that called?
Cosine? Sine.
That's a sine wave. And what's an interesting thing that we have with regard to a sine wave? We have a frequency. We have a frequency of the electricity that is coming out. And typically in the United States, this will be 60 hertz. So we then replace our battery with the person getting very tired of turning the power back and forth and back and forth and back and forth and back and forth. And we replace that with something that looks like this, which is a sine wave. This is an AC current source, AC voltage. In the United States, we have a nominal 120 volts AC power supply. If you were to measure the voltage coming out of the wall socket, you would see that it says we are a 120 volt power supply. And if you had a frequency meter, you would see that it is approximately 60 hertz. So flipping back and forth, making one complete plus and minus 60 times every second. Okay. So does the resistor that's in our circuit care?
No.
It does not care. However, what does the resistor in the circuit experience? What does the voltage look like? What does the voltage look like? It looks like that. The resistor is going to experience how much voltage right there?
None.
Zero.
Zero. It's going to experience no voltage at all. If it has no voltage, how much current is going to flow?
None.
None. That's right. How about right here?
None.
None. How about right here?
Zero.
Zero. And how about right there?
Same. Yeah,
Same.
zero.
Okay. How about at this point up here? The orange point.
Gotta give me another number somewhere on there.
Well, but is it going to be high or low?
Oh.
High.
It's going to be high.
High. How about right here?
Low.
No, it's also going to be high.
Also high.
Oh, high.
But it's also going to be going in the opposite direction. So
Oh.
it's going to be going this way some of the time, and sometimes it's going to be going that way. Now, the interesting thing about this is that we start looking at power, right? When the voltage is aiming this way, then the current goes that way. When the voltage is aiming this way, the current goes the other way. What is the formula for power? Come on, other part of the law.
Equals EI.
Okay. So let's look at this part. Okay, so we have a plus times a plus. What do we get? What's a plus times a plus?
A positive.
Okay. How about for the other part?
It's also positive because
we have a minus and a minus. So we get power being positive all the time. In other words, it doesn't matter which way the current's flowing, the power adds up. So we get peak power at these points, at the green points, and we get no power at the other points, which I'll just use a little black dot. So what does that mean? Do we have a constant power flow?
No.
No, we don't.
You have an average.
You have an average. Yeah, okay. This average has a name, which is RMS, which is root mean square. And it turns out that when we say that our voltage in the wall is 120 volts AC, that is our equivalent voltage. If it were DC, that would make the same amount of power as this thing. So when we actually take our meter, we would see if it read RMS power, it would say it's 120 volts. If we were to measure this point, it would actually be plus 170. And this point down below would be negative 170 volts.
I thought I understood it.
Because a sine wave of that size generates as much power as 120 volt DC. That's why they call it that. That's why they say we have 120 volt circuits. And this is something you don't have to know this for class, but it's important to know just when you stick something into the wall.
So that 170 volt, the negative and the positive, that's the DC, you mean then?
No, that is the voltage at that particular point. If you were to look at the peak voltages in the wall circuit, that's what you'll see. As it goes, it rides up and down. Okay. You actually peak at 170 and negative 170.
And then a black line right through the middle, that would be the 120.
That would be zero.
Son of a gun.
Yep. That would be your 0 point. If you were to map it out, you would get that. DC, it would be 120 volts. So in other words, 120 volts DC is the same power capability as 120 volts AC RMS, which is root mean square. And it deals with averaging over time. Anyway, you don't have to know that for class. You do have to know that for your general license. It's important to know if you're plugging something into the wall. And everybody does that. So, okay, but the important thing is that since we're talking about AC, what is the frequency of our AC? 60 hertz, and it's at 120 volts AC RMS. The important thing to know is that because it's the equivalent of 120 volts, we can still use all of our standard power calculations using 120 volts. So all of our, what's Ohm's law again?
Pi. No.
E equals IR.
E equals IR. You notice that this keeps coming up. And what's the other one?
The
E
power
equals
pi.
IE.
P equals I times E. For the most part, you can use that 120 volts. So if I have a circuit that has, it's plugged into the wall and it says this is 120 volts AC and this is a 120 volt resistor, or sorry, 120 ohm resistor, I can say what is my average current. What formula do I use?
1 amp.
E equals I times R. E, I, R. Get used to drawing that circle. You want to figure out my current. Cross it out. I is equal to 120 divided by 120 is 1 amp. And it turns out this is 1 amp RMS. So it actually goes up and down in the sine wave as well. But you basically just say 1 amp. We're all working in that same language now. So your RMS is nice because it means you can use your standard Ohm's law calculations for it. All right, so how about a 5-minute break? Everybody good with that?
Yes. Yes,
Okay,
definitely.
so I can keep going. So 5-minute break.
Brain break.
Hello, everyone.
Howdy, howdy.
Good news, everyone. Anyone get the reference there?
Good news, everybody.
Good news, everyone. You're going to the planet Vergon 6. Or Ebola 9, the virus planet.
Great series.
Oh, that was our old crew. Poor fellows. Didn't even know what happened to them.
Classic. I guess they're doing another season with Hulu, so that's cool.
What?
They're
There's
doing
another one?
I guess they said so, yeah. And the King of the Hill is already picked up. They're already done.
I look forward to seeing another Futurama season.
Absolutely.
Although they did end it the right way, so I don't know what the season's going to be.
I don't know if I ever went. I don't know if I ever sat. I'm sure if I open up my Hulu, I'm sure I've watched every episode, but I don't know if I sat there and digested every episode.
Mm-hmm. Okay, here we go. We're moving on to the next thing. So, we beat resistors to death, right? Well, fortunately, not everything in the world is a resistor, because a resistor is a linear device in that what does Ohm's law say? Everybody? E is equal to
MC squared.
That's also true. E is equal to I times R, and P is equal to I times E. Okay, so for a resistor, that is resistance is the ability of something to block the flow of DC. So resistors follow DC. Now, they also follow AC. AC, DC, resistors don't care. It's a linear device. Whichever direction it's flowing, they're going to react the same way. Fortunately, does everybody remember this little thing that I drew that looks like this? Remember that about an hour ago?
Yeah.
What's that thing called?
The finger thing.
Electromagnetic wave.
That's an electromagnetic wave. Okay. As it's traveling this way, it has an E field and a B field. And if you're going to ask why it's B, that's because apparently Maxwell wasn't sure he was working with, and he started with A and worked through H. He wasn't sure what the fields were going to be called. So that's how we ended up with a B field being the magnetic field. I actually had to look that up. I never really knew why. They just told us that it's the B field. Okay, so with an electromagnetic wave, we obviously must have something that causes this. So, as it turns out, electrons moving make a magnetic field, and an electron sitting still makes an electric field, just in space. Well, all right, that's all well and good, but those are kind of boring. So we have to figure out some way to make things move back and forth. Because stationary, like what happens if this electron isn't moving? How much magnetic field do we get out of it? We get none. So we have to figure out how to make this stuff actually work for us. So, as it turns out, there are other devices that we can use. Resistors are kind of dull. This is known as a capacitor. And this is known as an inductor. A capacitor has capacitance, which is the ability to store electrons. Resistors are real time. They don't store anything. Capacitors have the ability to store electrons. These are actually metal plates that are separated by a distance. The bigger they are, the more capacity they have to store electrons and thus store charge. An inductor kind of works in the opposite. What happens is that in an inductor, what happens is you have a current flow through it, and you get a magnetic field that forms into like a coil shape. And this stores energy in a magnetic field. This has inductance.
Now, is a choke the same thing as an inductor?
Yes. Mostly. It depends. It depends.
Just how it's used.
It depends how it's used.
Gotcha.
Okay, a capacitor, we use the letter C for capacitance, and it's measured in farads, named after Michael Faraday. Inductor, we use the big letter L, and this is measured in H for henries, named after Joseph Henry. You know, the great thing about being a scientist back then in the 1800s, early 1900s, is that if you did some work, you got units named after you. And we still know them today. So farad, Henry, ohm, volt, amp, you know, they all got stuff named after them. All right, so we have these two devices, which are now a little bit different than a resistor. So we're going to clear the screen, and I'm going to draw a capacitor. Okay. So a capacitor, if I hook this up to a source of electrons, the electrons come out of here. What will happen is these are full of negative charges and positive charges, and the current will start to flow. As electrons make it to this point, they will populate completely that plate. What will happen is the electrons, because you now have a negative charge, will force electrons away from here. The electrons will then migrate to there, and you'll end up with a net positive charge over here on the other plate. What do positives and negatives want to do?
Touch.
They want to attract each other. That's right. So now you have these two plates which are positively and negatively charged, which are trying to physically meet, but they are being held apart by the fact that you have filled this gap either with air or paper or something like that, which doesn't conduct, and it doesn't fall, it doesn't crush. So the space is maintained. And if I remember right, force is equal to K Q1 Q2 over R squared, if I remember right. So basically, that is a physical force that is a function of those charges being near each other, those Qs. The more charge you have, the more force there is between the plates. The more force there is, the more energy that's there. Essentially, a capacitor is a way of storing energy. And
so
it's a way of.
I'm sorry. How is that not also a battery?
A battery is chemical storage. This is
Gotcha.
This is essentially physical mechanical storage.
Gotcha.
They can serve the same function, except that with a battery, you have typically a lot of electrolyte, a lot of materials in the cell that will allow you to run for a while. So let's take a look at this right here. So let's say that I have disconnected the power supply, right? And I've disconnected the wires. What's going to happen to all those charges?
They'll start dropping.
Stay.
Where do they go?
They dissipate in the heat?
No, they have nowhere to go.
They stay.
Capacitor will stay charged up. If there's no place for them to go, they just stay charged up. That essentially is a battery, and we use this for certain things. This can be known as an ultra capacitor if we have a very high capacity one. And we do use that for storage of charge for large amounts. Typically, those require a very high dielectric constant, a lot of space. So typically we don't use them for a battery, but you could use them in place of a battery. What happens if you hook this up to a resistor?
It'll dissipate its heat.
Drain
start
to zero.
drawing.
Yep, and then you'll start to dissipate your current. You'll dissipate it through current. Eventually all the power will go away. But for the time being, you've got a little bit of power stored in there. So that's okay. So that's that's the whole point of a capacitor, to store energy in an electric field. So let me ask this question. We're going to take this capacitor and we're going to hook it up to something a little more interesting. We're going to take this capacitor and we're going to do this with it. So we have our pluses and minuses. This goes plus, this goes plus, this goes minus, this goes minus. When we first hook it up, we're going to get current flow. Then, as it sits there and it fully charges up, if this is completely full, how much more current flows? We get nothing.
Same.
We get
None.
nothing. It's full. It's full. The room is full. We get no current flow. So essentially, this now looks like an open circuit. If we were to, let's say we had a mystery circuit behind a wall, and we have an ohm meter, which is essentially like this. Oops. We have a voltmeter and an ammeter over here. So we had a mystery, our voltmeter or our multimeter, which measures volts and amps. And here's it has an internal battery and it tries to charge something to see how much current flows, and it goes full current and then down to nothing. That means that there's probably a capacitor over there that's charging up. If we actually hook up an ohm meter to it, we will actually see that happen. It'll look like a very low resistance and then change to a very high resistance in a second or two. That means that we're actually measuring a capacitor over there. That actually is on the test. So, okay, so now what we have is we have our battery charging up our capacitor. Once it fully charges, nothing happens. What if I were to take this and now switch it so that our plus is over here? What would happen to the charges that are sitting out there on the capacitor? They would instantly run back to the battery and then get erased and then get replaced by these guys. And then once they're fully charged, what happens?
Everything stops.
Everything stops again. Okay. So what's this thing called where I am taking this battery and switching it back and forth?
AC.
That's AC. I'm intentionally switching it back and forth. Do you think it is possible for me to choose a capacitor with a suitable capacity and a frequency at which to switch this back and forth where the capacitor will never become fully charged before it switches back the other way?
Yes.
Okay, so what will it look like if the capacitor never fully charges up? There will always be the flow of what? Current. If there's always current flow, what is that the equivalent of?
Magnetism?
No. If there's always current flow, that looks like this. If there's always current flow, it would be a short circuit. If there's no resistance to current flow, that's a short circuit, right? If I were looking at this behind a wall, I would assume that there was a short circuit back there if I hook this up to AC. If I hooked it up to a circuit that switched back and forth and the current always flowed, no matter what happened, that is the equivalent of a short circuit. At high frequency, a capacitor looks like a short circuit. At low frequency, looks like, which is like no change, an open circuit. Magic. Just by changing the size of the capacitor and by changing the speed, the frequency at which the power supply changes back and forth, I have changed how the thing behaves. Does that make sense? Okay, I see you shaking your head no.
It will, I'm sure.
No, well, I mean, let's go over it again. I mean, here's what to think about. If you do something, you don't know what's on the other side. If I hook up a power supply or a voltage to a couple of terminals on a wall and someone says, guess what's on the other side? And I always get current flowing back and forth without any changes. What must be on the other side?
A resistor, right?
No.
What's it?
What doesn't resist?
A short.
A short circuit. Something with no resistance doesn't resist.
Okay.
It must be a short circuit on the other side. By changing that, by selecting that capacitor and by selecting the frequency, I have made it so the capacitor never gets the chance to fully charge up. As far as I know, that might as well be a short circuit. If no one told me what was over there, it might as well be a short.
So it's a practical application of something like that to filter certain frequencies.
Yep. Yep. Okay, so now we're going to go to the next thing, which is this. That's our inductor. So an inductor ultimately is just a piece of wire. So if we try to push electrons into a piece of wire, what will come out the other side?
Electrons.
Electrons. So at DC, it's just a piece of wire, which is basically a short circuit. For DC, it's basically a short circuit. All right. As we do that, this forms a magnetic field in loops around it. So that forms a magnetic field, which looks like that. That's also known as a solenoid. That's how we make an electromagnet. An electromagnet is a direct current passed through a solenoid, which makes a magnetic field. This has a north and a south. We can do this with a little battery and a nail, and we can use it to pick up paper clips. Or if it's a really big electromagnet, we can use it to pick up entire car bodies and dump them into the crusher.
Can you not have an electromagnet with AC?
You can, but then you'd have to make sure that the poles would have to switch, and it may or may not work depending on what you're trying to do. It's easier to do it with DC.
Can't you use a bridge rectifier to do that?
You could, yeah, but that makes it DC.
True.
Essentially. Okay, so what we now have is we have created an electromagnet. What is represented by those lines going around it?
Magnetic field.
Magnetic field. Okay. What is stored in that magnetic field?
Electrons.
Electrical energy.
There is energy stored in that magnetic field. Okay. Where does that magnetic field energy go if you suddenly pull the current away from the circuit? and say, we're not going to we're not going to deliver any more current.
Doesn't it collapse?
Well, it's energy, right? It does eventually collapse, but it's energy. Where does it go? It can't just dissipate into space. Where does it go?
Back into the circuit.
How? There is no circuit anymore. It doesn't exist anymore.
Does it?
That's a fundamental problem. Because now I have these leads that come down to here, and they go into nothing. And I have all this energy, and it has nowhere to go. So what it attempts to do is say, okay, this energy, it has to go somewhere. And what happens is that the voltage, when that happens, builds on these 2 points, and it gets bigger and bigger and bigger until
wave collapse?
It catches fire.
you get a huge spark.
Oh, like a coil.
Like a coil.
Ignition coil.
What do you know? Guess what this is? It's a solenoid. What's at the heart of an engine ignition system?
It's an inductor.
It's an inductor. Okay. So what you get is a really big spark. That energy does not want to be dissipated. Similarly, it doesn't really want you to take this current and suddenly switch it back the other way, because that's even more of an insult to it. It's already happy, fat, dumb, and happy, sitting there putting energy through one direction and creates a magnetic field. And now you're telling it, not only do I want it to disappear, I want it to switch back the other way. All right, this is a huge insult to it, and it has to generate. So it fights back against you trying to do that. It tries to put a reverse voltage across where you're putting the current into in the first place. So it resists the change. The higher the frequency, the more it fights back. The more frequently you try to do it, the more it fights back. So if I were to take my battery again and hook it up to a wall, connect it to here, and I find that because it's always fighting back, I get no current at all. What must be on the other side?
Open circuit.
An open circuit. The higher the frequency, the more open the circuit gets. So for AC, an inductor is an open circuit in the extreme. Remember, for DC, it's just a piece of wire, so it's a short circuit, which is completely opposite of how the capacitor worked, isn't it? Capacitor was the opposite of this. So if I were to draw this, so if I have a capacitor and an inductor for AC and DC, capacitor for AC is a short, and capacitor for DC is an open, and an inductor for AC is an open, and a short for DC. It turns out that there is a term for this. We use the letter X, which is reactance. It's measured in ohms. And this is a component of something called Z, which is R plus IX. R is resistance. That familiar resistance, that's measured in ohms. And there's that reactance. So resistance is how something behaves in the presence of DC. Reactance is how something reacts to AC. Z is known as the impedance. And this Z is how something, a component, reacts to whatever voltage is applied. So that's really AC, DC, whatever. In the for the sake of this class, impedance is how something reacts to the presence of AC. And it's essentially how it impedes the flow as opposed to resists the flow. My guess is that they couldn't come up with another name. They had to think of something that was like resistance but different. And as it turns out, what ends up happening is that, how about a resistor? Does a resistor care whether something's AC or DC?
No.
No. So a resistor just has resistance. However, a capacitor or an inductor has this property called impedance because it has this property called reactance because of how it responds to alternating current. And as it turns out, there's, of course, a mathematical formula for it. For a capacitor, it's 1 over 2 pi fc, and for an inductor, it's 2 pi fl, where f is the frequency and pi is good old pi, 3.14159266535. C is the value of the capacitance. L is the value of the inductance. Those are both defined by the physical components themselves. So what you can see from this is for a capacitor, what happens if the F gets really big? Then you get something huge in the denominator and it goes to 0. So if you get it in the inductor, it gets really big. So a capacitor for a really high frequency goes to 0, it becomes a short, and for an inductor at AC, for really high frequency, it becomes an open circuit because the impedance goes super big. Well, actually now, as it turns out, there's even more to it that makes this really interesting and cool. Because now we have determined that not only are they like that in the extreme, but in those areas that aren't extreme, we have other cool things happening because we have those formulas that guide them. And those, when frequency is not 0 or infinity, it is somewhere in between, where they sort of act like both. And as it turns out, our impedance is actually able to be drawn by that on that familiar circular system again. Oops. Where we have R going to the right and X going like that. They're actually perpendicular to each other, which is why there's that little letter I right there. So you can have like 4 ohms of resistance and plus 3 ohms of impedance. And by the Pythagorean theorem, your impedance is 5 ohms. And there's an angular component in there as well, which causes the voltage and the current by Ohm's law to be out of phase with each other. It causes something called a phase shift. But you don't have to know that until the extra class exam. But again, it's good to know that it exists because this they do bring up in here. As it turns out, a capacitor, this is the formula for impedance of a capacitor. And this is for an inductor. I don't like the way I drew that number 2. And notice that one is positive and one is negative. So is it possible to take these two things, put them in line with each other in a circuit? They add together, these impedances add together. And because one is plus and one is minus, is it possible to make them so that this and this are completely equal and opposite?
I would think not.
You can.
You can.
You can. You can make them equal and opposite to each other. If they are equal and opposite, they cancel each other out. If they cancel each other out, what happens to the impedance?
It goes away.
Goes away. Z.
So that's a bandpass.
Z equals ZC plus ZL at that point is equal to 0. Your impedance at a particular frequency is nothing. What does it mean if something has no resistance or no
short
impedance?
Circuit.
It's a short circuit. And as it turns out, that is frequency is equal to 1 over, if you calculate it out, 2 pi square root of LC. So what are the only things that you have to pick to make that work? L and C. Capacitor and an inductor. And guess who can pick those? You can pick those. You can pick those. So by choosing your components, what you can do, this is known as resonance frequency. The same way that if I grab this cup, let's see if it'll do it. Let me turn on my musical thing. Can everybody hear that? Did I pick that frequency? Did I pick that note?
Sort of.
No, I didn't. I mean, I can hit it with anything. And it makes the same note. What makes it make that note?
The resonance.
The resonance, which is defined by how the cup was built in the first place. I had nothing to do with it, but somebody designed this cup.
Well, couldn't you, if you hold it in a different place, change the vibrations? No.
Makes the same sound because it's defined by the device itself. Somebody built this cup using specific parameters. If they built it differently, it would have a different ring. The same way that if we look at this circuit, by picking the L and the C, that's how it responds to different frequencies. It naturally passes certain frequencies, which means that if I have a map of frequencies that goes from 0 to infinity, and I look at how something passes through, I get nothing, 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 until I get a really big spike, and then it goes back down on the other side, and then nothing, 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 nothing. So if that's true, what would happen if I had hooked up that circuit to a power supply that made a frequency right here? What would come through?
Nothing.
Nothing. How about if it had a frequency component right there?
Nothing again.
Nothing. How about up over here?
Still nothing.
Still nothing. How about over here? Still nothing. How about if there was a frequency right here?
Bandpass.
That would be a pass. It would allow it to pass through. By selecting my components, inductors, capacitors, I could pick a frequency to allow to pass through. Let's say that this is human voice, or let's say this is a whole bunch of radio frequencies. What am I going to hear out of all of those?
Just that little specific spot.
Just that little specific section that went through. That is a band of frequencies. This is known as a band pass, and this is a filter. Similarly, by doing this, if I put energy into a circuit that is built that way, it has a natural resonance frequency. By changing this, by changing these values right here, I can make them variable like this. That means that I can adjust them. What would happen if I built this the same way? I would change the frequency at which it operated when I hit it. I can actually make something that oscillates, vibrates at a certain frequency, and I can have it be changeable. Like if I could add another weight to the bottom of this, it would probably change how the note came out. If I changed, because the frequency is f is equal to 1 over 2 pi square root of LC, if I change either one of those, L or C, I change the frequency and I move this pass band or band pass back and forth.
So is this how we tune a radio to different frequencies?
Now it becomes tunable. Now this is a tunable band pass. Okay, so does anybody now see how that could relate to what we were doing in the first place? Remember what we were doing in the first place? We had this. Remember that sine wave traveling through space? We have that electromagnetic wave traveling through space. It has a frequency. What if there is another wave traveling through space with a long wave and a very low frequency? And then there's another one traveling through space at a very high frequency. And they're all on top of each other. This is what the world actually looks like. This is what is passing through the world all the time, every single day. How do you pick which one you want to listen to? You run an antenna that receives things, that can look at all of these different frequencies, and you run it through a bandpass filter, and you filter out the ones that you don't want, and you allow the ones that you do want by changing these values of capacitance and inductance. And that allows us to see what we want to see. Similarly, if we want to make a particular frequency and stick it out there into the world at this frequency, we're going to add it to the mess. How do we do that? We use this device called an amplifier, a transistor, and we hook it to like something like that, which provides feedback, and we use that to generate, let's say, feedback, so that we have a self-amplifying thing, and by defining those values, we can change the frequency of the signals that come out of that get bigger. And then we can use that frequency that comes out of it as the basis for the signal that we put out into the world. Capacitors and inductors, just these two little devices that look like this, are the basis for everything tunable, for the basis for all radio. And that's why we spend time on it.
With your little diagram of the amplifier down here in the bottom left.
Yeah, that's probably not drawn right.
Well, conceptually, that's grounded to the earth on the right side, and then passing through the earth back into another an inductor?
Right. And there's a power supply that's injecting power into it, but it naturally, by choosing those particular frequencies, by choosing those devices, it naturally generates a frequency. It is preferable to the circuit to allow frequency of that or energy of that particular frequency to be created.
So with walkie-talkies, they're going to be broadcasting to an actual tower and then getting sent out of it. But the actual radio towers, they have to be grounded to the earth as a base. No. You said no. Okay. Sorry, there's so many concepts I'm trying to wrap my head around.
Mm-hmm. Well, I mean, a lot of this really is magic. What's important to remember in all this is that we make and pull out radio waves through the use of capacitors and inductors. They are the tools that we use in order to do this. All right. Questions? I know there's a lot. It's a lot of material. It does get easier, I promise. Okay, so now we're going to add another device. We're going to add a thing because we had these things called conductors and insulators. And okay, what's a conductor? Conductor passes electrons very easily. An insulator gets those electrons and blocks them. Well, now we're going to add something called a semiconductor, which kind of allows electrons to go and kind of doesn't. Some common ones are silicon, germanium, and it turns out that these are kind of special materials because they have a halfway full shell of electrons. So they can kind of go either direction, depending on whether or not you throw it a little bit one way or throw it a little bit the other way. So what we do here is we take a block of silicon and we kind of we kind of tilt the table a little bit. We throw in a little bit of phosphorus or boron, which has a slight lack of electrons. And so we call this our P side because it's slightly more positive. And then we put on the other side some materials that have a few extra electrons. So that's slightly more negative. So we have a P and an N back to back. And what happens now is that if we try to push electrons into here, they will encounter a brick wall. Unless we push really, really hard, they will encounter a brick wall. If we try to push electrons in this way, if we get the voltage up to a certain point, they'll go. It'll actually go through okay. So what ends up happening at that point is that we now have a block of something that allows current to flow. Actually, I drew that backwards because they get thrown in like this. That's actually the positive electron direction, if I'm not mistaken. No, this is the positive. That's the good electron direction. But again, thank you a lot for everybody who got current backwards and made us live with this forever. Current is backwards. So what essentially has to happen is that you end up throwing some P's into here because that's a lack of electrons, trying to push it through the P, and then eventually if you push hard enough it'll get through to the other side. But it won't work the other way. So what you end up with is a device that looks like a one-way street sign. This is known as a diode, and it has an anode and a cathode. And if you were to draw this, I'm still looking at the whiteboard. Can everyone still see the whiteboard? If we were to draw this, it would look like this in physical terms. It has a stripe on the negative side, and current, if you put 7/10 of a volt on this side compared to the other side, you will get current to flow through it in the forward direction. If you try to reverse it, you won't get any current through. So the important thing here is now to note that we now have a one-way street. Well, if we have a one-way street, we can do some really cool stuff with that. Because if we have, let's say, AC goes like this, where it goes positive and negative. Okay, so now we're going to draw this AC circuit right here. and hook it up to a diode like that. What happens when we are positive over here? So for the time that this is positive, current flows. So all the stuff on top, those are all good. But how about when it reverses? We change all the signs, plus, minus, and we have minus and plus, and now we're trying to flow it back that way through the one-way sign. That doesn't work. And now since that doesn't work, what we end up with is this being wiped out, and we have electricity, we have a voltage that looks like this. What is that? Considering that it's always positive? It's always
DC ripple?
positive. That would be ugly DC. That is ugly DC. It's always going in the same direction, but sometimes it goes to zero. But it never switches back the other way. So if we were to take this ugly DC and instead use that to charge up a capacitor so that whenever it got to the peak, the capacitor would be fully charged, and then when it got to the bottom, the capacitor would try to use its charge and send it out here, it would hit the brick wall, but it would still allow current to flow this way. So then if I looked at it at this point, which I'll use a green dot, it would look like this. So I would say that's less ugly DC. Okay, so now I can hook this up to another device, which is actually a diode running backwards called a Zener diode. Because for everything you draw, there's got to be, an exception to it. Essentially what this does is anything above a certain voltage, it says, okay, I'm just going to take it and send it down to nothing. I'm going to burn up the power, and I'm going to take that extra voltage and send it away. And it basically does this. So our voltage now is completely flat and above zero. What is that? That is DC. Where would you find one of those?
Rectifier?
That is a rectifier. It's known as a rectifier, but where would you actually find it? You have
Well,
one.
if you talk alternators.
You have one powering your computer.
Oh.
That is a half-wave rectified power supply. That, because most power is delivered to your home in the form of AC, our electronics work on DC. That is a way of converting our AC current in our wall to our DC current on the other side.
That's what this is doing? This bad boy?
That's doing. Yep.
No kidding.
Yep. In fact, if you hold up the specifications on to the screen, and we get them in focus, we can see. Let me see if I can make it big enough. If I pin it, pull it away slightly. There's a lot of writing on that.
I know.
But you will see that it says input 100 to 240 volts, for instance. If you take a look at the backside, it'll say input 100 to 240 volts AC.
Yeah.
And output like 19.2 volts DC at 2 amps or something, 40 watts or 60 watts.
Yeah, 65 watts.
65 watts.
Yeah.
And it's like 19.2 volts DC. So that is your DC power supply. Now, it is quite likely that instead of a single diode in there, there's a diode bridge rectifier, which is going to be more efficient. That uses 4 diodes. And essentially what you have is this, and then you have a load over here, and you have 1, 2, 3, 4. So your path goes like this, and then it comes out this way, and then goes back in this way and then out this way. And then the other half of the time, let's see, the other half of the time it comes out this way and goes this way and this way and this way and this way. I have to draw it like that sometimes. And so that's a full wave bridge rectifier. The benefit of that is that you have 4 diodes, which is a little more complex, but bridge rectifiers are easily available. They're readily available in integrated circuit packages, in very, very high current formats, and because there's basically 2 different paths for the current to follow depending on which way it's going. They are a lot more efficient.
And hence they don't need a capacitor.
And they don't need a capacitor, yeah. And in fact, I think I drew that backwards. Let's see.
Because the current always lines the path forward.
There we go. There we go. It goes back that way and then back that way. There we go. Right, so there's always a path to the load through a pair of capacitors. And that's known as a bridge rectifier. It looks like that. I just drew 2 of them backwards. Okay. Let's see. Next, how about transistors? Okay, transistors. A transistor is a 3-terminal device, and notice that this right here kind of looks like a diode. A transistor has 3 terminals, the base, collector, and the emitter. This is known as a bipolar junction transistor, or a BJT. The function of a transistor is that essentially this part of it is a one-way street. That is a diode. But it's special in that internally, when this path is open, what you end up with is this much larger and slightly isolated path being really open. So if I put, let's say, 0.7 of a volt here, and I have this at 0 volts, what I will get is an enormous amount of current flowing from the collector to the emitter. And so what I would typically do is put a resistor across that and maybe use that for something, and this would be a power supply. The benefit of this is that I can, by controlling what's happening on the base, I can control what's happening with this potentially enormous amount of current, which is somewhat isolated. This can be used as an electronic switch. By turning it on and off, by controlling this tiny little voltage on the base, I can control what happens across the big side, the big copy. So as an electronic switch, that allows me to turn something on or off. The other interesting thing is that, let's say I set this to 0.7 volts and then I add a tiny little ripple on top of it. So it's 0.7 volts plus some tiny little ripple. Well, I will get maybe 200 times the size. I will get a voltage plus a bigger copy of the tiny little ripple. The tiny little ripple could be my voice. So if I have this 0.7 of a volt plus this tiny little ripple representing my voice, what am I going to get going through the other side? If this on the other
side, an amplified
side,
voice.
If this is 200 times the size, I'm going to get an amplified voice. Can anybody think of any practical applications for that?
like a megaphone?
Yeah. Or
Okay.
any kind of amplifier. A transistor is the basis for amplification. The other cool thing about a transistor is because it can function as a switch, we have a couple of different ways to use this. So a transistor will typically look like this. Here's our input and here's our output. Below 7/10 of a volt, we can put the voltage, we can increase it, and then nothing happens until it gets to this point and it turns on and we get a linear relationship, and then at some point you can't get anything more out of it. You just can't squeeze any more output out of it. This area is known as the linear region. The reason we like that is because if you're making a copy of your voice, does anybody want to hear a distorted version of your voice? I certainly don't. All right, so we would use the linear region, and the way we would do that is we would pick a voltage where we would be right in the linear region, so that small changes in the voltage would cause big changes in the output, but would be linear. Below a certain voltage, we would have the cutoff region, in which case the output is totally off. And up here we would have the saturation region. The combination of those two makes for a really good switch. Can anyone think of something that might use the function of a switch being on or off, or 1 or 0? Can anyone think of a good application for that? Something's either 1 or 0.
I mean, binary code is the only
Binary code. This
Okay.
is the basis. This is the basis for switching in computers. This is the basis for all digital logic.
Yeah.
Now, it turns out that this particular transistor, which is known as a bipolar junction transistor, because it requires current to be flowing, is not particularly efficient in doing this. It was the first one developed, but it's not all that efficient. It was later determined that, oh, well, instead of that, we could do a circuit that looked like this, where we could simply change the voltage here. And what does this look like, everyone?
A capacitor?
That looks like a capacitor, doesn't it? Because it basically is.
Yeah.
And a capacitor works by an electric field. Well, this is actually known as a field effect transistor. There's the field, and by changing the voltage that's applied to the gate, as it's called, that changes the source and the drain path impedance. So, by changing the voltage on the gate, that allows a copy, or on and off, to exist between these two terminals. And that is known as a FET. Now, what's the advantage of this? How much current flows into that gate once it's at the full current, or once it's at the full voltage?
None.
None. Okay, what does that mean as far as power dissipation? If there's no current, there's
No power.
no power. And if there's no power, that means there's no
Frequency?
heat.
Heat.
And if there's no heat, how small can you make them? How many transistors can you pack in one little place?
Oh, you can stack them on top of each other.
And you can stack them on top of each other. And
CPU.
you can put them in. You can make them on silicon wafers, and you can make 1 billion of them on a chip because they don't burn up any heat. And this is the basis for all of our digital electronics, the field effect transistor. Now, it turns out that they're also particularly good for power. There's something called a MOSFET, which is a metal oxide semiconductor field effect transistor. There's also a whole bunch of other different versions of FETs out there, which are excellent amplifiers and excellent switches because they are very, very efficient. Okay. Everybody enamored with transistors now?
So why would you ever use a BJT?
Um, they're cheap. They're easy to build. They're easy to work with. I mean, a 2N2222 is a very, very cheap and ubiquitous transistor. Field effect transistors are a little more static sensitive. That's one thing, because it's an electric field. So if you like hold it in your hand and you walk across the floor and you pick up a static charge and you're charged up to 20,000 volts, you can blow up a FET. It's unlikely, but still, you know. All right. Let's see. Any questions before we move on from that? Okay, so we're going to talk about this. This is another fundamental of electricity. What is that?
That's the
What's that called?
Inductor.
That's an inductor. Yep, just a coil. Okay. If we put DC through it, whoops. If we put DC through it, we get magnetic field lines. If we have something that is a piece of steel or something, and it gets pulled by the magnetic field lines, what happens to this circuit right here? It clicks in because it pulls it down.
It's a relay.
That's a relay. That's what we do. This is a relay. It's an electromagnetic switch driven by a coil. Okay. Another thing that we can do with these is that we can take this relay, or for instance, we can actually have two circuits that get pulled in. We can also do this with basic switches. We can have it so when it's not active, this other circuit is functioning. So the number of functions is known as a throw of a switch. The number of circuits are the number of poles. So if anyone's ever heard of a single pole, single throw switch, that would mean you have one circuit and it only has one active state. You can have a switch that is a DPDT. That is a double pole, double throw. That's two circuits and two active states. You can have relays that work like that. You can have hand-operated switches that work like that. Okay. Now, what we're going to talk about before lunch is we're going to draw this thing again. All right, what's that called, everyone?
An inductor.
An inductor.
An inductor, okay. You put current through an inductor, what does it make?
a magnet.
A magnetic field.
fields.
Okay. So what we're now going to do is we're going to blow this up slightly and we're going to make it a big coil. Big enough for me to draw something in. So what we're going to draw now is something called a ferromagnetic material. Ferro means iron. Ferromagnetic means that it conducts magnetism. It's magnetizable. So this is now a ferromagnetic material. So we have now taken our coil, which makes a magnetic field, and notice what we've now done with it. We've taken that coil and wrapped it around something, which is made of iron or steel. And those materials tend to conduct magnetic fields really well. They constrain it. So what you end up with in this case is that your magnetic field instead of going and making loops like this, now the magnetic field is making a loop that kind of looks like this. It is more conducive to making a field that looks like that, that gets constrained within that material. Well, that's great, right? We have a couple of uses for that. Number one, if we make this material such that it tends to just circulate and dissipate energy, this is a choke. We can take AC, because we have AC energy, and we know that at high frequencies, a magnetic field, a coil will act like a dissipator of energy. It doesn't like to conduct them very well. So essentially that will cause a blockage. So we can use this as a choke. This is known as, this is something that will essentially kill very high frequencies. We can also, at lower frequencies, selectively pick our stuff so that we're going to pick a different color here. Well, if a current makes a magnetic field, what do you think a magnetic field would be able to make on the other side?
Another magnetic field.
No.
A current. Yeah.
If a current makes a magnetic field will make a current.
Yeah.
So by having a current flowing into one side here, we end up with a current that is flowing out of the other side. And if we assume that there's no energy loss, right, we're going to assume 100% efficiency in this case. Because in reality, we're at like 98, 99% efficiency for something like this. What would something be used for like this? This only works for AC. When would we ever use something like this?
Is that a regulator?
It's a transformer.
That's a transformer. So that is a transformer. It's essentially a magnetic. It's a ferromagnetic core with a coil on the inlet inlet side and a coil on the outlet side. They're called primary and secondary sides. The primary coil current generates the magnetic field, and it's used by the secondary side. So it turns out that the voltage ratio is proportional to the number of turns around the coil, complete turns. So if I have 100 turns over here and 100 turns over here, and I have 120 volts and 120 volts over here, I will get the exact same voltage out the other side. Why would I ever want to use that? Why would I ever want to do that?
To be able to transport energy long distances?
Yeah, but why would I ever want to use the same voltage on both sides?
Do you want to isolate?
Yep, perfect. Yep. This is known as an isolation transformer. If you ever wanted to separate what's happening on the inlet to what's happening on the outlet, that's called an isolation transformer. The other thing we can do with this, if we want to pick a different voltage or turns ratio, we can go and we can say that this is on the other side, this is, let's say, 10 turns. Okay, so the voltage is proportional to the turns ratio. If we have 100 turns and 120 volts on one side, we have 10 turns, and how many volts on the other side?
12 volts.
12 volts. Why would we ever want to use that? Remember, this is 12 volts AC. I'm showing you right now.
Step down transformer.
A step down transformer. There you go. That's what creates the low voltage AC in your power supply. There's a small transformer in there that converts 120 volts to 12 volts. Step down.
Okay.
All right. So other uses of such things. So let us say that we have a voltage out here of 12 kV and 1,000 turns. Where would you find that?
On the utility pole.
Yeah, everybody look.
Substation.
Actually, no. Just look out and look out on your street if you have above ground power lines. That's why you don't touch the above ground power lines because they're carrying 12 kV. So you have a transformer that is supposed to make then 120 volts for use for your house. What would the turns ratio be? This would be a 100-to-1 ratio. How many turns on your side?
10?
10
No.
turns. That's it. So long as it's capable of handling the amount of power that you need to drive your house. So why does the power company want to transmit power at 12,000 volts over long distances?
Because there's energy loss.
Because
it's insulated.
No, resistance in the wire.
Right,
E
yeah,
equals
yeah.
IR, P equals IE. It comes back to what law?
Ohm's law.
Everything comes back to Ohm's law. That's why the power utilities want to be able to. That's why they want to send power at very high voltages, because for the same amount of power, they can do less current. That way, resistance in the wire doesn't mean as much, which means they don't get as hot, which means that the power lines don't expand and sag, which means you don't get short circuits, which means higher reliability. When you get out to the really high voltage power lines, like the big transformer you'll find in the substation, you'll get something like this.
500 kV.
765 kV down to 13.8 kV. They're sent at ridiculously high voltages. The reason they're sent at such high voltages is because if you look at Ohm's law, P is equal to I times E. If you throw, and E equals I times R, if you throw 1 amp, 1 amp at 765,000 volts, that's a lot of power. All right, but where's the extra power coming from? Isn't the gain in voltage compensated by a drop? What was the rest of that? I didn't see it. And I lost it. Hold on. Where is the extra power coming from? Isn't the gain in voltage compensated by a drop in current, meaning power is constant? The power that you get is supposedly constant. Who eats the power? Who eats the power losses? Who eats it? Who pays for it?
We do.
That's right, we do. Because the electric company charges us for the power, right? The more efficient they are, the less they have to charge us for the power that they waste getting power to us. So we want them to transmit power at as high a voltage as possible. That's why some of the new DC power lines, DC transmission lines that are being built are in the 1 megavolt range, 2 megavolts, because the higher the voltage, the lower the power, or the lower the losses. And remember that, high power losses are a very, very, very bad thing, because that means that your power lines get hot, and if you look at case studies, that copper expands, aluminum expands when it gets hot, which means that those power lines, when it's a really hot day and everyone's using their air conditioners, and you have really high demands, you not only have high demands pulling a lot of current, but then you get really high temperatures. It's like 115 degrees in Arizona, and those power lines sag. And when they sag, they get close to each other. And when they get closer to each other, what happens? Or they get closer to to a tree, and they arc to the tree, and then the power line shuts down, and then you have a fire, right? So there's all kinds of problems. So that's why this stuff is all very important. All right, let me just make sure that we didn't really miss anything. We covered radio waves characteristics, switches, tuned circuits. Okay, so there's a special kind of diode which we can use a lot of. Everybody has one in their phone, I think. It looks like this. It's essentially a diode with an additional phosphor and a clear shell. This is known as a light emitting diode. The purpose of an LED is to generate light when it's turned on instead of just turning on. Okay, so what I'm going to do is I'm going to share this screen because I think it's more useful than anything I could draw. And everybody has it in their book anyway, so. All right, this right here. All right, so this is on page 29. This is a simple drawing, schematic drawing for a power supply. This is not actually how you'd build it, but this is essentially all the connections that you would make. So notice going from left to right, you have number one is a plug, number 2 is a fuse, 3 is a single pole, single throw switch. What was number 4 again, everyone?
That's an insulator.
Number 4?
Transformer.
Transformer. Number 5?
Diode.
A diode acting as a rectifier. That's a half-wave rectifier. Means it's making things better. Number 6 is a capacitor being used to smooth things out. 7 is a resistor so that you don't burn up number 8.
That's another form of diode, right?
That's a light emitting diode. That's an LED. LED
Oh,
is indicating that the power supply is turned on. It just lights up. Number 9 is it changes it's a potentiometer or a variable resistor which changes the load resistance. And number 10 is that kind of backwards looking Zener diode. Which notice that sort of has a letter Z. If you turn on your side a little bit, it could be construed as a letter Z. Right? That's a Zener diode. That's a backwards diode that's used for voltage regulation. And they're rated in terms of power and stuff like that. Okay, so this circuit right here, number 1, we kind of drew that a little bit, but we didn't quite finish it. This is a simple transistor. Number 2 is a transistor. It's a bipolar junction transistor. In particular, you notice that the arrow is pointing outward. Would everybody agree that the arrow is not pointing in?
Yeah.
Okay, good. Because the way a transistor like this is specified is either PNP or NPN, depending on how they're built and sandwiched together. So if it's not pointing in, NPN, that is an NPN transistor. That's the easy way to remember that. Essentially, what happens is that the transistor is split so that what's coming into the base from the resistor at number 1 passes through the emitter, which is the arrow outward. That current opens up the channel from the collector, which is at number 3. That's a lamp. And number 4, which is the power supply to the battery. That creates a circuit from number 4 to number 3 and through number 2. And you end up with an electrically controlled switch. You just turn the light bulb on. It's an almost pointless circuit, but that's what it does.
So is a PNP drawn with the arrow facing in?
Yes, it is. Exactly right. And that's because the device itself is built backwards. And since it's really a diode, that's why it's drawn that way. Okay, so right before lunch, math for electronics and conversion of electrical units. Okay, so powers of 10. Powers of 10 are very important. Giga, mega, kilo units, then milli, micro, nano, and pico. So it is important to kind of gauge whether everybody is comfortable with exponents. So we're going to spend just a minute on this. So number 10 is extremely important because 0 represents a decimal place. It's a space filler. 10 compared to 100 is a pretty significant change. Compared to 1,000 is another significant change. The way that we typically represent things that are big is just by adding zeros. The way that we represent things that are small is by adding zeros to the left of them. At some point, the number of zeros that we're filling in becomes a ridiculous number. Let's look at a billion. Okay, that's a stupid number of zeros to have to carry. It's a waste of time and space. So what we can do now is say we count 1, 2, 3, 4, 5, 6, 7, 8, 9, and it turns out by coincidence that if we have 10 times 10 and we have times 10 9 times, well, that is equal to that same number. And there are 9 of them. So we can now say that we have 10 to the 9th power, which means 10 times 10 9 times. It turns out there's that 9, and there are 9 zeros. So we can now say that we have this base right here, which is 10, and the exponent up here. So now we can represent this in what's known as scientific notation, which is 10 to the 9th power. The same thing on the bottom. We have 1, 2, 3, 4, 5, 6 decimal places. Well, we move the other direction there. So that's to the minus 6, because as it turns out, minus 1. 10 to the minus 1 is the same thing as 1/10. So 10 to the minus 6 is 1/10 times itself 6 times. So that is then 10 to the minus 6th power. So by looking at that, we can now see that wherever we see a 10 to the minus 6, we can replace it with the little letter mu, which means micro. So if we have 10 to the minus 6th henries, that's 1 microhenry. They are the same thing. This is easier than doing 10 to the minus 6th, which is much easier than doing this over on the left. The same thing up top. We can say that this is 1 gigahertz because we have 1 billion hertz or 10 to the 9th hertz, or we can replace 10 to the 9th with the big letter G because that's what it means. The other thing we can do with this is we can sort of work backwards and say, well, okay, let's say that I had 300. And you know what? Let's make it a little bit easier. Let's make it 100. And I started at a value of 1 and I ended up at a value of 100. How many times bigger did I get? Well, it's 100 times, right? I think everybody will agree it's 100 times. How about if I started at 1 and went up to a billion? That would be a billion times. Well, again, we're starting to get a little bit silly with these zeros. Well, okay, how about if I were to say that I wanted to create a shorthand, a shorthand notation to say I just want to keep track of the exponents. Well, then this would be a 2. And this would be a 9 because I took 10 to the 2nd power, and this was 10 to the 9th. Well, so that would be a 2, and that would be a 9. This was developed by Alexander Graham Bell. And of course, because of that, he named the thing the bell to say this is the exponent to which 10 has to be raised to get the difference between the end point and the starting point. So by shorthand, he said this difference of 100 times is a gain of 2 bells. This gain of a billion times, because it's 10 to the 9th, is a gain of 9 bells. Well, as that turned out, the bell was not a particularly convenient unit to use because there were still a lot of decimal points. So what came out of that was something called a decibel, which we use for everything. A decibel is 1/10 of a bell. So you would take this 9, and now that becomes 90 decibels. You would take this 2, and that becomes 20 decibels. And now we have some units that people seem to like using, and you can say, well, there's that 9, 10 to the 9th power is how many times bigger it was. And conveniently, this is the best part of this. If we have a situation where we have 100 times, and then another 100 times, and then another 100 times, and then another 100 times, this is 10 to the second, and 10 to the second, and 10 to the second, and 10 to the second. And by convention, if they're all multiplied, all we do is we add our exponents, and that becomes 10 to the 8th power. We're just adding zeros. Well, so if we're only keeping track of the 2's in bells, then we just add them together. So 2 plus 2 plus 2 plus 2 is 8. If we happen to be doing decibels and we're doing tenths, it's 20 plus 20 plus 20 plus 20 is 80. And this is what we actually do today. This is how we measure something called gain and something called loss. So if we start at let's say a milliwatt of power, that would be the unit itself. So we call that 0 dBm, which is 0 dB compared to a milliwatt. We use that as a reference power level. And we end up at 10,000 watts. Well, okay. So let us conveniently calculate. This is 0.001 watts. How do we multiply by tens, steps of 10 to get up to 10,000? Well, we go 0.01, 0.1, 1, 10, 100, 1,000, 10,000. Every time we multiply by a factor of 10, that's 1 bell, or 10 decibels. And that's 10, 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 and that's 10. Add them together, 1, 2, 3, 4, 5, 6, 7. And if I did it right, I get a gain of 70 decibels. And in fact, that's actually correct. And compared to the original milliwatt, I could say my power level is now 70 dBm compared to a milliwatt. The other convenient part of this is that it is approximately true that the number 2 is approximately equal to 10 to the 0.3 power. That is approximately true. So if I care about bells, the bells would be right there. So that would be 0.3 bells. That's not that helpful. However, by going with decibels, well, there are 3 tenths, which is 3 deci. So a gain of 2 times is approximately equal to 3 decibels. And this shows up everywhere in radio and electronics and science and a bazillion other fields. So if I go from, let's say, a starting point of 1 to 80, I can take steps by factoring and say 1 goes to 2, goes to 4, goes to 8, goes to 80. Okay? Well, 1 to 2 is a doubling. That's 3 dB. This is 3 dB, 3 dB, and 10 times is 10 dB, and then you can add them together and get 19 dB. And that is really cool because I can go and get my calculator out right here. Let me share my calculator. and I can go through, and now you can all see my calculator, and I can say, okay, it's a gain of 80. I want to take the log times 10, and what do I get? I get 19, which is basically exactly what I just got on paper. So all of these things that you do looking for, things that make signals bigger, that like an amplifier, we measure the gain in decibels. An attenuator or attenuation or signal loss, we measure in decibels. Basically, we measure everything in decibels. And it all comes down to the same use of scientific notation and exponents. And because we don't really care whether or not it's 18.3 or 19.1, you can pretty much do it just on a scrap of paper. And those of us who've been doing it for a long time, if we almost never need to know exact calculations. It's all just rule of thumb. What's cool about all of this then is that if somebody gives you a system, because if you're on the air, part of doing ham radio is understanding the basis of how a radio system works. If I have a transmitter which is 1 watt, and you are allowed to use a calculator on the test, and here's a piece of cable. This cable is rated as 3 dB of loss per 100 feet, and it's 50 feet long. That would mean minus 1.5 dB. Connected to an antenna which has 7.5 dB of gain and a path loss of minus 160 dB. And I want to point out what's significant about that minus 160. If you kept the decimal points, it would be 0.00000000000000001. That's why it's more convenient to use this shorthand notation, because we don't have to keep track of all those silly zeros. And then we have another system on the other side, which has another antenna, which has, let's say, 16 dB of gain, and an amplifier up here, which has plus 18 dB, and then a cable, which is the same, minus 3 dB per 100 feet, and it's 50 feet long, which is minus 1.5 dB, and then we get down to our radio at the bottom. Okay, so starting at this point right here, compared to a milliwatt, which is 0.001 watts, this would be 30 dBm. And we're just going to go around and add and subtract. Minus 1.5 plus 7.5 minus 160 plus 16 plus 18 minus 1.5. So I grab my calculator and we go 30. Let me share this. Minus 1.5 plus 7.5 minus 160 plus 16 plus 18 minus 1.5. Okay, so what is that number?
19 decibels, same as the other one.
No, negative 91.5 dBm. So if I have a receiver that has a minimum discernible signal at minus 100 dBm, do I hear something on that side, yes or no?
Yeah, yes.
This system works. That is why we do this stuff, because what if it didn't work? What if you found going through your map of the system that this didn't work? Could you fix it?
With Ohm's law?
Not Ohm's law, really. Could you fix it by replacing stuff?
Your antenna?
Sure. Sure, you can figure out what's wrong and make it better and fix it. And did you have to go through any did you have to like look at that minus 160 dBm and carry all those decimal points? I mean, sure, I've got a lot of experience doing this stuff, but it took me 2 minutes, right? Carrying all those decimal points, that would have been a 20-minute job. This shorthand notation is incredibly powerful for figuring out how to work on systems, how to make a radio system work. So you say, okay, where's the applicability to my situation? My situation is I work with CERT, right? I want to be able to provide emergency communications in times of emergency. Where's my applicability of this to my CERT group?
Figuring out what kind of maybe amplifiers that you might need to be able to transmit and receive over a certain coverage area that you're working.
Right. Yeah. What is my coverage area? What's my distance? What is my terrain? Do I need a better antenna? What if I go on that hilltop? I mean, search and rescue. What if I am the one who needs to get rescued? Where do I go so people can hear me?
Higher is better.
Yeah, higher is better. When would you go? When would you want a better antenna? When would you want a directional antenna, which has gain in one direction versus others?
A repeater?
You could, if you had access to a repeater, how do you get better access to that repeater? How do you get yourself heard? You look at the situation and understand that the math says that the way that you're set up right now, it's not going to work. Being able to understand how all these things fit together, which is better, going up on a hilltop or taking a higher gain antenna with 50 feet of cable that you can then throw up in a tree? And the answer is, I don't know. But if you know how that cable behaves and how much gain that antenna has, it might be better to climb up the tree. It might be better to go find a hilltop, or it might work just fine. You guys ready for lunch?
Yes, sir.
All right. Half an hour?
That sounds good.
Okay. I'll be back around 1:30 Pacific time.
I'm sorry. Could I ask you just one quick question?
Sure.
It was just concepts again about the power lines. When you were saying, in Arizona when it's hot and they start to sag.
Yep.
Are the power lines sagging because heat is making them expand and they're getting more lax?
Yes.
Or is it also because, like, I know energy has mass, energy has weight.
Not so much in this.
Not so much. It's not. There's not too many electrons in there and anything like that. Okay. It's
There's
just
no accumulation. No. It's just that the metal is getting hot and it stretches. It expands like, it just physically expands. It's not so much stretching, it's just expanding, because things expand when they get hot, which makes it sag. And if it wasn't close to a power line, then if it wasn't close to a tree, then it'll probably be okay. But if it was borderline close to a tree, now it's arcing to the tree.
Gotcha. Awesome. Thanks for all this, man. This is awesome.
Glad to help. Questions before we go? All right, let's go eat. buddy. All right. Well, who's got questions? Oh, there's another dog. Come here, Oliver. Oliver, come here. What?
This is Cooper.
Where? I'm trying to figure out what happened to mine. Oliver, come here. Come here. Oh. Look, Oliver.
Look, he's 2,500 miles away.
Mm-hmm. Look, Oliver. There's a dog.
He's a good dog.
Oh.
Attention hound.
Mm-hmm. Oliver, look. Look. Oliver, look. Look. What's that? There's Cooper. Look, Oliver. There's Cooper. Look. He doesn't care. Oh, yes, I know. The things we do for love. Okay.
Hey, how often do you do this sport?
It's hard.
I worked in broadcast for a long time, and I'm learning stuff that I've never learned.
It just takes, it takes a lot of prep on my part just because it's a lot of people and a lot of it's easier than it used to be, but it's just 12 hours of effort plus a lot of preparation. So
Will you be sending us the recording of this class?
I'll be sending you the link to it. Yeah.
Amazing. Thank you.
Mhm. Well, I mean, in any vocation, you're taught what you need to know, right?
That
Right.
would be correct.
So, do you need to know the theory at the very bottom? Yeah, probably not, right?
No, I worked in it when I was young. I didn't even know what I was doing, to be honest with you. I shouldn't have been playing with the stuff I was playing with, but
I mean, you
I
had to get
worked
a
on
commercial
a
license to do it.
55,000 watt transmitter.
Yeah. But I mean, you needed to get a commercial license to do it. It was really so you don't kill yourself, right?
It was pretty much just because I could get away with walking on the transmission line and not breaking anything.
Right. So I got to go to before they tore it all down. It was a naval transmitting station in Annapolis, and it was a 1,200-foot tower, and the tower was shunt fed, and it was also fed with open wire feeder, if I'm not mistaken, and because it operated on VLF.
Is that where you could hold this fluorescent bulb in and it would light up?
Uh-huh. And they said if you ever went out into the field when it was transmitting, you had to be careful in how you stepped because the points on the ground were going to be at significantly different potentials, and you'd get kind of like a current running from one leg to the other and through your groin and yeah,
Get
crazy
RF
stuff.
burn.
Yeah, I've done that by touching something. Actually, I got that from a handheld radio. My sweaty hand. All right, everybody ready? Half hour's up. Oliver, you need to sit. I have to go to work. Okay. Oh, he's taking his ball and going away. What a good dog. All right, so questions and stuff. No questions? There's got to be questions.
Hello, can you hear me?
Yep.
What's DBI?
Oh, yeah. Okay, here we go. Okay, so that is an excellent question. Okay, so there's a couple. Okay, so there is a DB, there's a DBD, a DBI, and a DBM. All right, a DBM is a power level because it's referenced to a milliwatt. So 1 watt is equal to 1,000 milliwatts. Agreed?
Yes.
So 1 watt
Yes.
is 30 dBm. That is actually a reference power level. So a dBm is a power level. All right. A decibel is just a reference from a general reference from one point to another. One ratio. Hold on. One thing to another. Okay, so that's just a decibel, right? Those are the ones we frequently use. Now, DBD, okay, that extra letter afterwards references something. That is a dipole. And we're going to get to that very, very shortly. DBI is isotropic. So those are specifically for use in calculating antenna gain. So a dipole antenna, yeah, we're going to get to it. I'll make sure we get back to it as soon as we get there. All right?
Okay.
Okay. All right. So now we're going to talk about antennas. and things like that. But in order to understand antennas, we need to understand current. So we're going to draw an antenna. Okay, so here's a piece of wire. What is the current at that end of that wire?
I don't know.
This is not a trick question. This is not a trick question. What is the current? It has to be zero. What is the current at this end?
Zero.
Has to be zero. And why does it have to be zero?
We don't see a power source.
There's nothing there to hold current, right? Current is electrons, flow of electrons. Every electron, by Kirchhoff's current law, as it's called, says that there is in a conductor there's no accumulation of electrons occurring. That means that for every current flowing in, there has to be one flowing out, which means the net is zero. Okay, so if I have an antenna that is just sitting there, an antenna is just a piece of wire, right?
Yep.
And what is this? What is that? That's just a wave, right?
A sine wave.
That's just a sine wave, right? Okay, so if I were to take this piece of wire, what points on that sine wave, which is just some random arbitrary sine wave, could exist at the ends if I draw the 0 points? It could be here, or here, or here, or here, or here, or here. And we don't really need to see all of them. Really, we're just basically looking at a section like that. So it could either be right there or right there. So let's just pick one. Now we're going to start on the other end. I'm not really sure, but I'm going to assume it's going to be symmetric. So we'll look at it like this and say we'll pick this one right here. Okay, so we have a little bit of a discontinuity here. And maybe it works and maybe it doesn't. But what we do have now is a wire that we're basically looking at our current profile for a particular wavelength, because this down here represents our actual waveform at a given frequency. And what's important about this is that these wavelengths that we're showing right here, like this is a physical wavelength. That is actually a physical thing, which means that if we have a particular piece of wire of some certain length, to see what it will look like on a particular wavelength, we can actually draw a current profile on it like we just did. So that is what that antenna looks like on a given frequency that we picked, just randomly. The only constraints are that because it's a piece of wire, it has to have zero current at the ends. We can pretty much arbitrarily decide where we're going to break it so we can put power into it. We could try to put power into it at the end or very close to the end, like here. We could pick somewhere close to the middle. We could pick like over here or over here. And what we would basically do is we then would take this antenna, split it like right there, take our feed line, which goes down to a transmitter, and this would have current going up and current going down at that point. What we now have then is the fact that at that same time, we not only have, so this is our current distribution. Notice we have these nodes where the current is zero, and these peaks, either plus or minus, where the current is big. we typically end up with a voltage maximum where the current is at its minimum. So the current, it might look like this. And since we've decided we're going to put power in right there, we have to look at Ohm's law again, and we're going to see, instead of what's Ohm's law again, everyone?
Isn't that V over
E equals I times R. You are to write this 1,000 times because you're going to use it all the time. E equals I times R, right? E-I-R. And if you want to be more general, it's not R always. It could be impedance. You could use Z. Z often simplifies to R. Well, we're calculating Z, which is the impedance, is equal to E divided by I. And we're going to look at this in a qualitative way. So right here, when you say that it's the voltage, which is in green, and the current, which is in brown, the voltage is pretty big, divided by the current, which is well, so that would mean that our impedance would be something that's big divided by something that's medium. That would be this kind of high. Isn't that a good technical term? It's kind of high.
Is there like a number that you're trying to match your impedance
There
to?
is. So what we're going to do is we're going to pick a different place and see what happens. So let's pick a different one, let's say right here. So right here we have voltage that is low, and high current. And we can go through and say Z is equal to low divided by high, which is
very small.
Kind of small. All right. So it depends what we're trying to do and how we're trying to feed it. Transmission lines are used to transfer power from a transmitter down here to an antenna. Because without an antenna moving power back and forth, moving electrons back and forth, we don't get any signal launched into space. And then we don't really have anything useful at all. So we're going to get into transmission lines because we've covered impedances a little bit. So a transmission line is, for the simplest way to describe it, two wires. And that's pretty much it. One is carrying current going up, and one is carrying current going down. And if we wanted to draw it the other way, we could do that too. One is carrying current going up, and one is carrying current going down. They're opposite of each other. So every wire is going to make a magnetic field. Because these are parallel to each other and in opposite directions, their magnetic fields look like this. And they cancel each other out. So this area with the parallel wires doesn't make any signal because it naturally cancels itself out. But what it does is it takes energy from one end and sends it out the other end. So when you start looking at this, you're like, well, how does that really work? Well, if no power comes out as in the form of radio energy, in the form of electromagnetic radiation, and you assume that these wires don't use up, but their resistance is fairly low, so they don't use up a lot of power in heat if it's good cable, where must the power go?
In the air.
It must go out the other end, which is kind of counterintuitive, but it actually works. So that being said, what if I were to draw? I'm going to redraw these parallel lines. Okay, every piece of wire actually has a little bit of this built into it. And what is that?
It's an inductor.
That's an inductor. So every piece of wire has a little bit of inductance, self-inductance, built into itself. Two pieces of wire that are separated by a distance can be modeled as what?
Capacitor?
That's a capacitor. So we can take our transmission line or our feed line or whatever you want to call it, and we can do this and model it like this. And it goes on and on and on and on and on. So, if that is true, then what do I have here? Kind of a tuned circuit.
Transistor?
No, that's two inductors and a capacitor. That basically.
So that means it could hold power for a millisecond or whatever.
It does. It switches power back and forth between the capacitors and the inductors, between the magnetic and electric fields contained therein. This is actually a tank circuit. Yeah, it's not tuned per se, but it does have impedance. But it doesn't burn up power in the impedance. This is a special kind of impedance called a characteristic impedance. It does not use power, but it has an impedance based on how it's built, what it physically looks like. So if I were to take, for instance, come on, delete for me, there we go. If I were to take two parallel wires and make a capacitor out of them, and then take another capacitor and do the same thing but make them closer together, would they behave the same way?
Like in a circuit, you mean?
Now, yeah, if I were to just look at those two capacitors and say, are they the same capacitor? They are not, because those plates are closer together. So they would have different capacity and different electric field, the ability to store different electric fields. Their capacitance would be different, which means that their impedances would be different. They are different things. Similarly, if I were to have another one that had them way further apart, like this, that would behave altogether differently as well. Now, at the same time, if I were to change the values of the inductors in the same proportions as I just changed those capacitors, the characteristic impedance would be exactly the same, because the ratios of how they behave are the same. And this is actually really important, because I could draw, let's say, two pieces of wire that are separated by a distance, or I could draw two really thick pieces of wire for instance, that are separated by a different distance. And that could say that if I went through calculations, this would be 450 ohms impedance, characteristic impedance. And this one would be 450 ohms, characteristic impedance. Which one's heavier? Which one's bigger? Which one can handle more? Which one can carry more power?
Well, one.
The bigger one. It's got bigger wires, so it has lower resistance, right? But fundamentally, they behave the exact same way because they're carrying AC and they're in parallel and their fields cancel out. There's another kind of feed line that we use that looks like this, and everybody has probably seen this at some point. You have this in your house.
Yeah, that's what I was thinking.
Yep, that's like cable TV coax. Coaxial cable. Okay, so cable TV coax looks like this. A cross section will look like this. So you have conductor, which is basically a shield. And then running through the center of it, you have a conductor. So this is, for instance, your current going up, and this represents your current going down. They're balanced, they're equal, total, because they have to be, and because it's an enclosed system, any fields that exist are inside the shield. So they would still cancel each other out. Now, what do you notice about them? Which one is going to be carrying a higher current density if the currents are exactly equal? The inside or the outside?
It would have to be the same, wouldn't it?
Well, no, the current density. The total current is the same, but the inside, because it's a lot smaller, the density of the current is a lot higher. So
that said, isn't the inside copper and the outside's aluminum?
yeah, but they both travel on the shield. They both travel on right near the outside, so it's all about surface area. So this is actually known as, if I were to draw two parallel wires like this is balanced line, and this is unbalanced, because the current densities are not quite the same. So coaxial cable, this is called coax. That's known as an unbalanced line. Okay, so similarly, what do you notice if I draw something that looks like this, where I have a conductor and a conductor around it? That's a capacitor. Instead of being plates, what I have is basically a vertical strip and like a cylinder around it. That's a capacitor. So that's a cylindrical capacitor. So that has capacitance, and that because they're conductors, they also have inductance, which means that it has a characteristic impedance. And as it turns out, if they're all in the same proportions, I can have coaxial cable that looks like this. Or I can have coaxial cable that looks like this. Who worked for a TV station?
Me, but our coax was made out of like 6-inch copper or 10-inch copper.
How big? Yeah. And what channel were you on? You're muted.
I think it was 67. It was 678 something.
678 megahertz. Okay. So as you change your frequency, so what you had was like 10-inch hardline, which is like basically a copper pipe. You can also
I think it was a big copper pipe, and the interconductor was like a
small copper
2-inch
pipe.
or an inch. Yeah.
Yeah, isn't that amazing? That was feed line because the frequency they were at was at 678 megahertz, and we're going to get to losses in a second about that too. So and how much power were you running? 55,000 watts?
55,000, 1.5 million after effective
1.5 ERP? 1.5 megawatts ERP, effective radiated power. Okay, so, how about if I said that this was RG8X, which can handle 500 watts and is 3/8 of an inch in diameter. And this has a characteristic impedance of 50 ohms. 50 ohms is what most ham radio equipment is. It's characteristic impedance of 50 ohms. This is his 10-inch hardline, which is basically copper pipe, inside copper pipe, and could handle 55,000 watts, and was 10 inches in diameter and had a characteristic impedance of 50 ohms. How can they both be 50 ohms?
The ratio is the same?
Ratio is exactly the same. This, the big one, is a big scaled up version of the small one. So what do you gain when you do that?
Oh.
Well, you gain power handling because the conductors have much less resistance, so they don't heat up as much. Because every conductor has some resistance. But they're both still 50 ohms. If you have a 50 ohm antenna, 50 ohm load, 50 ohm transmitter, everybody's happy. Now, the other thing is that as your frequency increases, your losses get worse and worse and worse for every cable. So I like to bring this up here. Okay, cable loss chart, W4RP. Okay, here we go. This is a very important kind of thing to understand. Okay, can everybody see that okay? Okay, so these are all, well, with the exception of RG6 and RG11, those are 75 ohm. Everything else is, notice, right across the bottom, impedance, 50 ohms. Let's pick a frequency. So we're going to go to our frequency spectrum and look at the 2-meter band, which is between 100 and 200 megahertz. In fact, it's 144 megahertz. Let's look at RG58. This is El Cheapo cable that we use all over the place. It has loss at 100 per 100 feet, somewhere in between 5 and 7 dB. So we'll just call it 6 dB. Okay? So we're going to go through a basic calculation here and say, here's my transmitter, and here's my antenna, and I live on the 2nd floor of a building, and this is on the 12th floor. All right, so 2nd floor to 12th floor. I have 100 feet of cable to get from that one point to that other point. I have chosen RG58, which has a loss per 100 feet of 6 dB. Okay, so if I look at 6 dB, thinking back to those things that we were talking about, 10 dB is 10 times. If I have negative, that's 1/10. 3 dB is 2 times. And these are just things to commit to memory. And that's 1/2. Okay, so if I have a loss of 6 dB, what does that mean for the first 3 dB? How much power goes away?
Half.
Yeah.
I lose half. So if I started with 1 here, after 50 feet, I'm at a half. Then I go through and lose another 3 dB. How much comes out the other end?
It's only a quarter.
It's a quarter. If I have a 10-watt transmitter, how much actually gets out the other end?
2.5.
2.5 watts. Where are the other 7.5 watts?
Lost in heat.
They heated up my cable. Okay, they might keep it from freezing in the winter. That's about all I can expect, right? So I burned up 7.5 watts in heat. Okay, so now let's instead take that cable, that system, and give me a 1,000 watt transmitter. How much comes out the other end?
250.
250. That's right. It's a proportional thing. So where's the other 750?
Making things very warm.
Making things very warm and quite possibly melting my cable.
Uh-huh.
Right? So I'm probably not wanting to do that. So what can I do to make things better? We're going to go back and look at the chart. Okay. All right. So could everybody see this when I was drawing it?
Yep.
Okay. So we're now losing 3/4 of our power in heat. And depending on what we're running, it's really, really wasteful. So let's get some 9913. This is good cable. How much loss do we get at 144 megahertz? It's between 1.4 and 1.8. So let's just assume that it's 1.6. Okay, so now we're going to go and unshare this. And I'm sorry if I didn't before. Okay, so we unshared that. And now, instead of that 6 dB of loss, we have only 1.6 dB. Total. So now, 1.6 dB, I'm going to go through and run it through the calculator so I get a good number. 1.6, 10 to the x. Oh, right. So that would be something on the order of, what, 70% that actually gets through, 30% loss? %. So 25% loss. So I have 250 watts just by changing cable. Instead of 750 watts, I have 250 watts getting lost in here. And 750 watts coming out the other end. So I've completely flip-flopped those. Thus the benefit of doing that. You know, when you start to look at cable losses and things like that, you start to understand why certain cables are good for certain frequencies. Typically, as you go up in frequency, your effects become worse and worse and worse. Well, okay, so yeah, so let's look at 400 megahertz. right? So,
Can I ask a quick question?
sure.
If your base unit was up on the 12th floor where
Then
your
you wouldn't have
antenna
a problem.
was,
That's right.
then you'd be all good.
Yes, that's exactly right. And that is why, hey, okay, so who operated the TV station?
I actually think I saw him stand up and step
Here
out.
I am.
There we
I'm
are.
here.
Okay. All right. So where was your transmitter with respect to your antennas?
Uh, our stick was six or not 600, 300 feet, and we might have had. It was a messed up situation. The antenna was right above the television station.
Okay. If you could have put the transmitter up on the tower, that would have been a lot better, right?
There'd be no way. It.
Well,
I mean, it had like three big, giant Klystron tubes.
yeah, okay. But one thing to be said about that is, yes, like there is there's a piece of equipment out there right now called an ICOM 905, which is kind of like an experimenter's box for 10 gigahertz. And anytime you try to have to put 10 gigahertz through transmission line, you're going to lose a lot of it. So it has a control unit and then it has an RF unit, and they communicate over either Ethernet or some other protocol, so that the transmitter is way up at the antenna wherever it happens to be. Now, of course, you have to make it waterproof, but it makes the system work. So yeah, that's exactly right.
I do remember we got water in the line one time, blew up a tube, knocked big holes in the transmission line. It was not fun.
So one interesting thing about transmission lines is that coaxial cable is great, but water destroys cable. Water is the ultimate enemy of cable. The other thing is that connectors somehow, for some reason, tend to vibrate loose. I don't know why, but they do. All right, so we are now going to talk about the things that those cables feed. So the fundamental antenna is known as a half-wave dipole. How long is a half-wave dipole?
Depends on the wavelength of the frequency.
That's right. Well, at whatever frequency and wavelength you pick, it is a half wavelength long, roughly. Okay, so what we're going to do now is take a look at the amateur bands that we have access to. And you guys, because I like having interactive classes, you guys are going to pick a frequency to build this on. All right, so pick one.
70 centimeters.
Okay, pick a frequency on the band.
Let's go with 443.
443. Okay, so let's build an antenna. All right, let's build an antenna. Half-wave dipole. Okay, so what's the first thing we have to do? We know the frequency. What don't we know?
The wavelength.
Wavelength. What do we know? We know the speed of light. So what's that circle that we make?
It wasn't pi, it was something else. I wrote it down.
So we got 300 F and lambda. You need to be able to make this in your sleep. All right.
When we divide 300 by half.
Well, we're gonna find the wavelength first. So, what is that?
So it'll be 0.67.
Okay. So that's one wavelength that's one wavelength in free space. Okay. So what are we building? A half-wave dipole. How long is a half-wave dipole going to be?
Half of that.
Half of that, which is
33.5.
Okay, 0.335 meters. Okay. Now, here's the tricky part. Whatever you come up with, you need to shorten it by about 5%. And that is because of the real world and the fact that there's capacitance and inductance, and it just turns out that it's a little too long. So you have to shorten it by 5%. That's kind of a fudge factor. So what does that give us? So like 0.32? Like 0.32? 1 part in 20? No, that's wrong. Yeah, like 0.32, right? Let's see. Make sure I got it right.
Yeah, it'd be 0.318.
Yep. Yep. Okay, so about 0.32 meters. Well, now we're going to, because we don't live in Europe, we're going to convert it 39.34 inches per meter, and we get 12.5 inches long. Okay, perfect. We know how long to make it. That's how long we need to make it. Okay, now what's important about a dipole, why is a half-wave dipole a fundamental antenna? Really the fundamental antenna. What does the current have to be at the end of any antenna wire?
0.
0. Okay, so it has to be 0 at both ends, and it's a convenient half-wave long. So we can do this, and we actually get up to its full peak and then down to 0 at the end, which means that we have maximum current. We are able to get the full maximum current there, and if we feed it at the center, we're feeding it at a current max, which usually translates to voltage minimum. And if that's true, what does Ohm's law say? What's Ohm's law again?
Still says pi.
V equals IR.
Yep, E equals I times, in this case, Z. So we need to solve for Z and say Z is equal to small over big. Because we don't know exact values, but we know we're at our voltage minimum and our current maximum. So small over big, which is small, which means that we're going to get some impedance that we can probably deal with when matching it to a 50 ohm piece of coax. And usually we can get away with that. Nominally, a dipole has a feed line, an input impedance of about 72 ohms. And that's because it's taking current and converting that current and movement of electrons into energy that's being radiated. A dipole is about 72 ohms. And that's actually a decent match for most coaxial cable. So, congratulations, you built your first antenna. Well done. So now we have a dipole. It looks like this. And this is a half-wave center-fed dipole. Okay. And we have a current distribution that looks like this, which is really ideal, so excellent. Okay, now, as the fields are generated, what ends up happening is that in order to model this, what you end up doing, I actually had to do this in school, is take a look at the approximate current in each part and figure out, given the fact that it's at a certain frequency and certain wavelength, at all points in space, what is the contribution of that current to that electric and magnetic field at all points in space? That does not sound easy, does it? And you know why it doesn't sound easy? Because it's not. However, it is convenient that we have software to do this now, as opposed to when I was in college, in which case we had to do it by hand. And what's now cool about this is the fact that we know that that half-wave dipole in free space generates a pattern that looks like this. Here we go. It basically makes a donut shape around the wire in the form of a figure eight. So that means that some of that energy is going to be coming directly at us. Some of that energy is going to be going straight up and down. Some of it's going to be going back away from us. And so if we were to now rotate this so that we're looking at it on its side, looking at it from the end, we would see that here's our dipole, and we would see that it makes a pattern that goes in all directions, but none of it is coming toward us. It basically makes a donut around the wire. It's a little hard to draw. I'll see if I can find a better picture of it. So one interesting thing about that is what happens to the signal that's going into the ground?
Bounces off the ground?
Some of it. What happens to the rest of it? It heats up the ground. Right? That's energy. It heats up the ground. How about stuff that goes straight up?
It keeps on going until it bounces off of something.
Exactly. It goes until it bounces off of something. And so this is not necessary. It's a decent antenna, but it's not the perfect antenna. There is no perfect antenna. But so stuff that we're doing basically now, some of that signal, especially at 70 centimeters, is wasted because it's going straight into the ground, and some of it's going straight up into the air. So what can we do with this antenna to make it more useful to us? Well, how about if we took this half-wave dipole and instead made it a vertical half-wave dipole? Which way does the figure eight go now? So what does the figure eight look like?
Horizontal.
Horizontal, okay. And since we are operating at 443 megahertz, and it turns out that at these frequencies, this is well into the UHF band. The UHF bands, we're going to get into propagation in just a minute, don't tend to really, unless you're trying to talk to somebody up in space, don't really have a lot of purpose for being shot straight into the air. And it turns out that most people who are on this particular band are going to be in cars or using handheld radios. Well, we talked about this briefly this morning. The direction of the wire determines what the electric field is. That determines something called the polarization. This is vertical polarization. Two antennas that are polarized the same are going to have an easy time talking with each other. So now if I were to draw this system, and I'm going to do it, put one over here and then put another one over here, are those polarized the same?
Yep.
Yes.
Yes, they are. Which means that the signals that are polarized in the vertical direction coming from one are going to get to the other one and be accepted very easily by that, which means that this system is really going to be good for one vertical antenna talking to another vertical antenna. That is probably why the TV, what did you have, like a 4-bay vertical antenna? on the TV station? Oh, you're
I
muted.
never got up. I never got up on
Okay.
top of the station.
It was
I mean,
very,
I looked at it, but it looked up, and then it looked like a cactus, is best as I could say.
yeah, but it was typically going to be vertical. The reason that something like that
Correct.
is vertical is because do you know where your viewers are going to be? Do you know where your listeners are going to be? They could be anywhere in the horizontal plane, right? The goal of putting an antenna tower way up high is so that it's way up high and that the signal goes out in all directions equally well.
Somebody told me the signal went out like a donut. I don't know what that meant.
What was it?
They told me the signal would go out like a donut. So if you're like really close, you didn't get it good. But
Right,
if you were out
right.
like
Exactly. So that was a vertical dipole. And in fact, that was probably a 4-bay. So it could be a 2-bay, 4-bay. That's basically dealing with, there's that donut shape, right? So if you are right below the donut, how much are you going to hear? You're right in the donut hole. There's nothing going up or down. It's all going out horizontally. So there you go. This one, there's something called reciprocity in antennas. If you have an antenna, its receiving pattern is the same as its transmitting pattern. It's important to note.
I have a picture of the donut if you would like to
Yes, I will let you
see
share.
here.
Go ahead.
It's in the book,
hold on.
actually.
Let me unshare this. It's actually in the book. That's cool. Hold on.
So it's in that ARRL ham radio licensing manual.
Oh, yeah.
If anyone has that book, in chapter 4 under antennas, and it goes through, and you can see where the donut.
Hold on. I'm trying to, there we go. Unshare. Okay, go ahead. Hold it up really close. Oh, there we go. There's a good donut. Yep. Because it's a 3-dimensional thing. It's like a fat donut or a bagel. Thank you.
Thank you.
Okay, so working from this now, it's important to note that now that we have this vertical polarization, okay, we can do other kinds of cool things with this too. If we have this dipole and we have another dipole spaced a certain distance apart, and these are connected to cables which are of different or same lengths depending on how it works, each of these provides a pattern, and these can either become additive or subtractive. So what tends to happen is that you get an additional 3 dB of gain by phasing 2 antennas together, which is probably what you guys did if you had a 2-bay. It squeezes the pattern even further down. Certain times, this is very, very important. Another thing we can do is we can take this antenna, which is a half-wave dipole, and we can add about a quarter wave behind it, a longer element, and then a quarter wave in front of it. We can add a shorter element. This is known as a reflector, and this is known as a director. And what happens is that there's one driven element which receives power, and these other elements here and here are parasitic, which means that they are basically in the field generated by the first antenna that's getting the power, and they actually are caused to resonate by that field. The one that's the reflector essentially causes signal going backwards to be absorbed and re-radiated in the forward direction, and then the ones that are in the forward direction cause energy that's radiated in the forward direction to essentially be caught and amplified and redirected in the forward direction. And the net effect is that instead of having the donut shape, what you end up with is a shape that looks like this, where you have a very significant amount of power going forward and a very small amount of power going backward.
Would that be like a dish TV broadcaster, a receiver?
That would be a Yagi. That would be a beam antenna.
Actually, it kind of looks like a UHF antenna for a television.
Close. A UHF. So that's another type. A Yagi antenna is specifically going to be designed for one frequency. So this will typically. So compared to this, how do you think this difference in performance is measured?
Gain. The spacing between the director and the reflector.
Decibel.
The spacing between the director.
It's measured in decibels. And in fact, compared to just a plain old dipole, this is measured in dBd. Does that answer the question about dipoles and what dBd is? In other words, it is so many decibels better than a dipole would be. Okay, now, here's another one. A dipole itself looks like this. There's another antenna which is known as an isotropic radiator, which has the same pattern in all directions on the sphere. This does not exist. When comparing it to that would be measured in dBi, where I is isotropic. It is an imaginary, idealized antenna that cannot be built. So a dipole has 2.15 dBi gain. So just a plain old dipole is 2.15 dBi, or decibels better than an isotropic would be. But again, an isotropic radiator doesn't exist. But sometimes you will see an antenna design specified in gain in dBd, and sometimes you'll see it specified in dBi. This gain in dBi will always be 2.15 dB better than it would be in dBd. So it could say 10 dBi. It could also be 8 dBd. That's the exact same thing.
If those can't be built, what is the what is the benefit of what's the benefit of this?
It's just, if it did exist, this is what it would be. It's a completely hypothetical thing that can't be built.
Huh. So it doesn't benefit the rest of the science really, and it's just
it's a reference point. It's a zero reference to start at. Because you might have an antenna that's 0.9 dBi. In other words, it's still a pretty lousy antenna, but it's better than it could be. Maybe there's really no good reference to have compared to a dipole. I mean, I've built antennas that are considerably worse than a dipole. I have one in my yard right now. I mean, I have antennas that are worse than an isotropic. It's negative gain compared to compared to an isotropic.
That last image you were drawing, that really with the reflector and everything, that really looked like a TV dish or something like that.
Okay, here we go. So this is a Yagi. Right, and each of these directors is about 5. This is not to scale. Each of these directors is about 5% short. And this is about 5% long. And this is the driven element. The number of directors you have, the more your gain. We also have something called a front to back ratio. And that's measured in decibels also. Front to back. And we also have a way of looking at it like this, where if this is the peak, and this is minus 3 dB, and minus 3 dB compared to the peak, that's known as the 3 dB beam width. And why do we use 3 dB? Because 3 dB is, or minus 3 dB is half the power. So that's a convenient way of looking at it. There's that 3 dB again. That'll show up, like I said, all throughout science everywhere. It's kind of like a staple of antennas. It's a staple of looking at roll off and gain of a filter and all kinds of stuff. 3 dB is used everywhere because it refers to half power. Okay, so dipole antenna. Now, TV antenna. Okay, so you may remember an antenna that looked like this, where they got a lot longer and a lot shorter. Anyone ever seen one of those?
Oh,
I used
yes.
to have one. Okay, if you look very closely, its feed actually looked like this. They were crossed elements, and the feed, every element was active. And this is known as a log periodic, or LP. And because the short elements were so short and the long elements, okay, here's the real reason to understand exactly what's happening here. Channel 2. What frequency is channel 2 on? And for this, we need to go all the way back to when we were looking at the NTIA chart. And you know, here's the thing. I don't mind doing this at all because it's all educational. I mean, this is all educational. It'll all feed into what you guys are learning. And I know that I have, you know, what, 12, 11 hours to teach, and I can read the whole book. I've heard it done on an audiobook in 2 hours. So we've got, you know, as I see it, we've got time to, you know, to learn this stuff. So I don't know. I don't want AI assistant. Hide. Okay, so I want to share that. Here we go.
Somewhere between 54 and 72.
Yeah, here we go. Okay. I don't know if I can stop AI companion. Sure. Okay, is that being shared now?
Not yet. There it is.
Okay, here we go. All right. So broadcasting, AM radio, there's broadcasting. Here we go. From 54 to 72, TV channels are 6 megahertz wide. Right? It's 4.5 megahertz for, what is it, for audio, and 1.5 megahertz for, no, 4.5 meg for video and 1.5 meg for audio. Basically, each channel takes up 6 megahertz. Channel 2 is from 54 to 60 megahertz. If we were to look at that and we got an approximate wavelength, the 6-meter band is at 50 megahertz. So 60 megahertz would be about 5 meters in length. A half-wave dipole would be about 2.5 meters long, which is about 8 feet. Right? You want some part of your antenna to be able to receive TV channel 2 because there is a TV channel 2. All right, so now you look at how this is all spread out. Channels 2 to 6 were in this region. Notice there's that little gap in there, but channel 6 was up here at 88 megahertz, or channel 6. Then there's something called VHF high. Notice this gets squeezed a little bit. It's only because it's of how it's represented. 174 to 216, this is channel 7 to 13. So 200 megahertz would be a wavelength of about 1.5 meters. So already we've got the need to have, let's see, 5 meters and then 1.5 meters. And
Sure.
now we're going to go down to UHF.
Thank you. Plate or a bowl, doesn't matter.
So here's the UHF channels from 512 to 698. So that is in the nature that's in the area of, let's say, 600 megahertz, which would be a 0.5 meter. Okay, so now having done all that, we want to have an antenna that can simultaneously receive those three wavelengths. How do you build one antenna that's tuned to be able to do all that? Those are very, very different, right? I mean, one wavelength is 10 times as big as the other one. So the way this works is that you have these very big antenna elements at the back and the very small ones at the front. And these are logarithmically related element lengths, such that at the very lowest frequencies, these other elements up front are extremely short and thus not going to work at all. So you'll end up with on channel 2, you'll have like, come on, there on channel 2, you'll have just those back two elements working. As you move to the middle, 1.5 megahertz, the higher in frequency you go, these big elements won't be in the picture at all. So that by the time you get up to like channel 7 or channel 10 or whatever, you'll be using those two elements. By the time you get up to the UHF frequencies, like channel 67 or something, you'll be just using those two teeny ones at the front. So now the question is, how good is an antenna in which you're only using two elements at any given time?
Not very.
But it's better than nothing. Because of the way it's all laid out. And we deal with this stuff all the time when designing antennas. This is known as a compromise. And it's a compromise that actually works kind of okay on a whole bunch of different frequencies. Like the gain is probably only like 4 dB because you're only dealing with two antenna elements on any given frequency. But it's 4 dB and we'll call it DBD. It's 4 dBd better than nothing. And it provides some gain on all of them. So that's a big part of the kind of stuff that we do. Because if we were just dealing with one set of frequencies, this is actually very instructive. Then the world, our antenna design world would be would be very different than this. This is how you could conceivably design an antenna that works on a whole bunch of different frequencies. And what do you trade off when you do that?
Power loss?
Performance. Exactly. So if you've ever seen an antenna called a disc cone, has anyone ever seen one of those?
Like the satellite dish on the lawns?
No, that's actually a dish.
Oh.
Here, I'll bring up a picture of one. Looks like that. Anyone ever seen an antenna that looked like that?
Never.
Look at the frequency range.
Yes.
Look at the frequency range. 100 megahertz to 3.3 gigahertz. That's a great antenna. It actually simulates a logarithmic antenna because of the spacing and the angles of the elements, and the fact that only a certain amount of the antenna works at any given frequency because of the spacing and how it's built. Now, what do you get from it? You get enormous functional bandwidth, right? What do you lose? What do you think the trade-off is?
Yeah, still power loss, right?
You get basically no gain, but it works okay for a whole bunch of different things. So, essentially you trade one for the other. And if you happen to live in an area where you have a scanner and you're nearby an airport or something, you don't need a lot of gain. You just want an antenna where you can hear a whole bunch of stuff. You live you live where there's a whole bunch of different repeaters on different bands, this can be a very decent antenna. You don't need gain in that situation because you're so close to everything.
Does gain equal range?
It can. You tell me. That's kind of the point of all of it, right? Because if you're looking at getting a signal from one place to another, and you have an additional 10 decibels of gain, that's the same thing as running 10 times as much power.
Doesn't gain amplify the signal?
Or fails to lose it.
Okay.
It's another way of just basically figuring out what your, like, okay, let's say you have two pieces of cable here's a good one. This question came up last year or so. Somebody was putting up an antenna, a piece of antenna cable to connect from their station to their little Yagi up in a tree. They'd hung it up in a tree or something. And it was about 40 feet. But all they had was a 100-foot piece of coax. They said, I don't really want to cut my coax. What should I do?
They coiled it.
Yeah, what does that do? It's 100 feet of coax. And they're using it on 70 centimeters. It's it's basically 60 extra feet of coax. And what does that cable do?
You're almost creating like an inductor.
Yeah, it's basically just loss. It's inserting loss into it. Everybody said, cut the cable. If you ever want to put it back together, get some connectors. Make two cables out of it and just use the short one. Because otherwise you're just burning up power. Right? Now, is that amplification of a signal? No, it's removal of loss, which has the same effect. Did that answer the question, kind of?
Yes, sir.
So gain can translate to greater range. The question is, do you actually need that? Right? And that comes down to, looking at the situation that you're in. There's a lot of, there's a lot of mathematical stuff that governs everything here. So, okay, other antennas. Other antennas, we've covered we've covered dipoles, we've covered Yagis. A Yagi is a type of a beam. How about an antenna that looks like this? And it has a signal that goes out that way. Anyone ever anyone ever seen a dish?
Microwave?
Yeah, microwave dish. This can have a gain of up to 30 dB in the forward direction, depending on the size of the dish and the wavelength that you're using. What is 30 dB? Let's go back to that calculation thing. So 30 is equal to 10 plus 10 plus 10, right? And every 10 dB gain is how many times? Come on, this is super fundamentally important. Every gain of 10 decibels is how many times?
10.
That's right. So we have 10 times, 10 times, 10 times. What do we get?
1,000. That's 1,000.
1,000 times. So if I put 1 watt in, what is my effective radiated power going up in that one direction?
30,000 decibel?
1,000 watts.
1,000 watts.
Right. I have an effective radiated power of a kilowatt. Legal? Sure.
Should be.
Yeah.
Yes.
What if I wanted to do moon bounce and I had a kilowatt amplifier?
Oh, I thought you were kidding about bouncing stuff off the moon.
No.
What?
People do it all the time. If I have a kilowatt amplifier and a 30 dB gain, what's my effective radiated power?
Megawatt.
1 megawatt ERP aimed right at the moon. No, people do it all the time. That's called moon bounce.
For amateur radio stuff?
Yep.
Wow. Okay. Wow.
Yep, it's called moon bounce. Do it all the time. I've never successfully done it. I know a lot of people who have. And a 30 dB gain is not unheard of for a good sized dish. And it used to be, has anyone ever heard of this place? Anyone ever heard of Arecibo?
Yeah, down in Puerto Rico.
Down in Puerto Rico?
The antenna collapsed.
Uh-huh. The Ham Club used to use the Arecibo telescope as a transmitting dish.
Thing was huge.
Yeah. And let's see, what was the antenna gain of Arecibo? 62 dB. So 62 dB. Let's calculate that. So how do you break that down? 10 times 10 times 10 times 10 times 10 times 10 times about 3. So 1, 2, 3, 4. Let's see. 300,000 times. So 1 watt in would produce 300,000 watts effective radiated power out. A kilowatt in would be 300,000 times that, so that would be 300 megawatts. They used to do that for moon bounce. By the time it got to the other end, you really didn't need much of an antenna to hear it, because there was so much energy bounced off the moon that even with all the loss of traveling through 500,000 miles of space, it was no big deal.
What kind of input power are you talking about to transmit that much?
Kilowatt.
Is it equal? Okay.
Kilowatt amp. Yeah, no big deal. Okay, so now we're covering the other type of antenna. Share webs. Okay, here we go. So we have this antenna right here. And this is a half wavelength long. What's that called, everybody?
Half-wave dipole.
That's a half-wave dipole. Okay, excellent. Okay, so how about if I take the bottom part completely off? It's not a half wave anymore. What is it?
Quarter?
That's a quarter wave, and it's no longer a dipole. It's now a vertical. But there's something missing, which is that the current still looks like this, but there's still the bottom half. It's gone. So what you now do is you take this bottom half of the antenna, which should be there, and you do this with it. You need something to effectively reflect the top part in the bottom. And that is, somebody said something called a ground plane, which is right. We use a ground plane, which is an electrically reflective surface like the body of a car or the ocean full of salt water. Essentially what you do is you take your feed line and you feed one part of it going up and the other part connected somehow to the body of the car. Or, if you want to be clever about it, you take a plate that's on a magnet and you put it about a quarter inch above the car body, above the sheet metal, and how does that energy transfer to the car body? If we were to zoom in right there, what would that look like?
That's a capacitor.
That's a capacitor, yep. It is capacitively coupled to the body of the car. So, You deliver power to the top part and then imaginary power to the bottom part. And now what does it look like? What does the antenna now look like?
Never
If I were
seen
to
that.
see this from way over here, from way over yonder, if I were to see this from way over here, what would I be looking at?
Half.
It'd be a half-wave dipole. I would be seeing a half-wave dipole. Essentially, if you want to try this, we can do a little trick. If I can find a reflective surface like this, let me unshare this. Okay, so I've got maybe something reflective right here. Oh, here we go. Okay, here we go. Okay, so I've got this, and now I've also got, notice, a reflection coming off of this reflective surface. If I do it right, how many lights do you see?
2.
Okay. Do you know, if I didn't tell you there was something here, would you know the difference?
Nope.
That there was something down below? So
Between light, no.
as far as the external world is concerned, there's nothing different. It's a half-wave dipole. The only difference is that when we actually build it and when we actually deliver power to it, instead of being a dipole which has a 72 ohm feed point impedance roughly, when we fake it out and put that second, and we put the reflective surface underneath it, it's no longer 72 ohms, it's actually 36 ohms. So that's our new reflective surface. And it's only 36 ohms. Now, one thing we can do with this is we can be a little creative in how we build it. And we can do this. So here's the vertical part. This is a quarter wavelength long. That's about 19 inches for the 2 meter band. And then we can take our 4 radials, or 6 radials, or however many we want, and bend them down at about a 45-degree angle. And if it were flat, that would be 36 ohms. A dipole, which looks like that, is 72 ohms. Essentially what we're doing is we're taking and splitting this dipole into a bunch of pieces and bending them upward. If it were completely flat, that'd be 36. So somewhere in between is 50 ohms, which is a perfect match to 50 ohm coax. And that's why I have one of these on my roof. And this cost me all of $5, including all the cable. Antennas are the single place where you can make or break a station and whether or not it actually functions well. Right? You can take as they say, you can take a $10,000 radio and hook it up to a lousy antenna and you have a $5 station. You can take a $5 radio and hook it up to a great antenna and you can have a $10,000 station.
So what is that antenna called there? That the quarter wave with the apron?
That's just a quarter wave ground plane. A homemade quarter wave ground plane. It's made with Romex. It's just made with solid copper from Romex. Yeah, from Romex wire.
Okay.
I think it's either number 10 or number 12. It's just solid copper. All right, so now we're going to talk about propagation. Okay, propagation is how signals go from place to place. So since the Earth is largely land and water, we're going to make it kind of dirt color and watercolor. Okay, so this is the Earth where we live, and now we're going to draw a couple of other things. So we're going to make it kind of like a light blue for the sky. Can you guys still hear me okay?
Yeah, clear.
Okay, good. Okay, so this is the atmosphere that we live in, and I'm also going to draw this big glowing ball of gas up in the sky, which is 93 million miles away. Okay, so we have a couple of things at play here. So we typically live in the very bottom part of all of this mess, right? So we're down here. And we live in the troposphere. And up here then is the stratosphere. And then above that is the ionosphere. Space nominally starts at about 50 kilometers up. That is basically the beginning of the ionosphere. So the ionosphere is now broken up into multiple layers. They are known as the D, E, and F1 and F2 layers. F1 and F2 sometimes join and sometimes are completely separate. So this starts at about 30 miles. This goes up to about 50 to 100 miles. This goes up to about 200 miles. And this goes up to about 600 miles, at which point you're basically in space. And interestingly, a lot of the satellites are up here. They're still in the ionosphere. So if you've ever heard, like there was a solar flare and a whole bunch of satellites are at risk, and that's because the Earth's atmosphere changes shape and size and density, and it actually causes satellites to slow down in their orbit because they're still technically in the atmosphere. In addition to just, bombarding them with radiation. Okay, so we have access to more than a few frequencies. So everybody remember this chart? This is one of those things that I sent everybody. This big chart here of all the frequencies that we can use. These frequencies all behave very differently. Up here at the very high frequency end in the UHF range, these are mostly line of sight. Line of sight is basically exactly that. It's where you have two people that can see each other, or maybe a little bit beyond the horizon because the radio horizon is a little bit longer than the light horizon. But essentially, they are line of sight, which means that your range is limited to a few dozen miles, essentially along the horizon. And that's known as line of sight. Beyond that, you also have this troposphere that we live in, which can sometimes do some interesting things with those frequencies. Once in a while, you will get a temperature inversion layer, which will cause signals to go up and get bounced around in between layers because of differing densities of the air, different refractive indices. Because remember, radio waves are really just longer wavelength light waves, and you might come down and be able to talk with somebody at a distance of, let's say, 200 miles, 300 miles. And that's known as ducting. So that's known as tropoducting, and there's something also known as troposcatter. But those are both in the troposphere, very low altitude, and those are typically VHF and UHF. Okay, here's another one that we have, which is the D layer. The D layer, all right, so it's important to, oops, you're right, you did not see my sketch. Okay, so thank you for that. So there's the, so there's the tropo. We have ducting and scatter that occurs at low altitudes. Then we go up. Stratosphere doesn't really do a whole lot interesting for us. There might be some ducting and stuff, but the D layer is where we have to start talking about how the sun and the earth interact. So the sun continually pelts the earth with all kinds of radiation, not just light. So the sun generates RF, radio frequency. It generates it generates UV. It generates infrared. It generates light, thankfully. It generates X-rays. And basically everything on that spectrum comes out of the sun and pelts the Earth all the time. Well, fortunately for us, we have an atmosphere that, for the most part, filters out the ultraviolet and the X-rays. What ends up happening there is that the hard X-rays and ultraviolet that make it down to the D layer generate this layer of absorptive material. Essentially, what happens is when you get high energy photons and they strike a nitrogen or an oxygen atom, they cause an electron to fly off, causing it to become ionized. So we end up with positively charged ions and free electrons floating around. There is so much in the way of that in the D layer, because the density is pretty high, that anything up to 10 megahertz during the day hits that layer and the energy just gets absorbed by all those ions and electrons. So it is basically like a death sentence for anything up to about 10 megahertz. This is why we cannot hear AM radio on the car radio during the day from anything more than about 30 miles away, because those signals are down in the 1.6 megahertz range. By the time they get up into the D layer, they get absorbed and we can't hear them. All the energy just disappears. So that's MF and like 3 to 10 megahertz. So that just gets absorbed by the D layer. What happens at night is that as soon as the sun disappears, all those ions that form down here go away. And all that absorption that was happening stops. So those radio waves that were basically blocked and absorbed from bouncing are now able to make it up to the high layers of the atmosphere, of the F layer, where they are refracted back down to Earth. And because they're at particularly low frequencies, this works at most times of the sunspot cycle and most times of the year. And if anyone's ever been driving down the road and gotten to listen to an AM radio late at night, you'll hear signals from 1,000 miles away. And this is why you hear signals on AM radio from 1,000 miles away at night, but you can't hear them during the day. Other frequencies, depending on how much ionizing radiation is striking the Earth's atmosphere. Yep. Oh, depending on how much ionization is striking the atmosphere, they will get up into that same area, and some will bend down, and some will go like this, and some will just shoot on through. Depending on how much ionization is occurring, which is dependent upon season, which is the tilt of the Earth to the sun, sunspot cycle, and time of day. So during the day, right after lunch, typically you'll get peak ionization directly overhead. Early in the morning, you haven't built up yet. Late in the afternoon, it starts to fade. At night, you get no new ionization, so you get a lot of recombination. So the density of all that stuff way up in the atmosphere tends to go down. For the most part, the maximum usable frequency is proportional to the density of the ions and electron clouds, which means that during the day, your maximum usable frequency is considerably higher than at night. And this is important because if you look at this chart, we're going to look at the high frequency bands. 10 meters, which is 28 megahertz, all the way down to, let's say, 15 meters, which is 21 megahertz. Those are basically daytime bands. 20 meters is going to be pretty much day or night, but then anything below that, 30 down to 160 meters, those are almost exclusively nighttime bands. The higher bands will also work better in the peak of the sunspot cycle. We are close. We are just past the peak of this sunspot cycle, which is an 11-year cycle. At the very peak, 10 meters was open to much of the world for much of the light daylight hours. At night, 10 meters goes away, 12 meters goes away, etc., etc. You can also end up in situations where you have something called the day-night terminator. If you look at a map of the Earth, half of the Earth is light at any given time and half of it is dark. If you send signals along that day-night path, you can go considerable distances around the planet. And give me a second here. Come on, why are you doing that?
So would you say that the lower the meter wavelength, the larger the chat room?
Ask the question again.
Like the lower the meter wavelength, the larger the chat room, the more.
When you say the chat room,
just like as far as just like the spectrum of people on the planet you're going to be interacting,
It depends. I mean, when 10 meters is open, you can talk, an entire hemisphere can have a common conversation. It's pretty wild. And when 10 meters is good, it doesn't take much. I mean, a few watts, and everybody can hear everybody. It's pretty amazing. So, okay, here's an example of what can happen at gray line, as it's called. Here we go. No, I don't.
Once you apply it, it's there to stay. Seriously, it's that permanent.
No, it's
so
not.
If you're...
Can everybody hear audio?
Yes.
Okay, I'm going to start that again. Listen very closely.
And 40, that's what we have right now, Roger. Thank you very much. Karen, the Yankee Julia, 0 Tango Tango, listening time for 20F.
You notice the echo? Listen for the echo.
Was ending Yankee. Radio Zulu 9, Yankee, power 9.
That is not an effect. I was there. That is not an effect. Anyone have any guess as to what that was?
He was hearing his own radio broadcast?
First, yeah, that was our transmission
from multipath.
Well, it wasn't multipath. It was a single path. It was gray line propagation where we had a single path that went completely around the world and would carry that frequency in both directions multiple times so that one signal could make a couple of passes around. And every time it came back over, it would get heard again. And it would be, and one full trip around the Earth is 140 milliseconds. So
it wasn't like feedback.
No, that was actually hearing us multiple times. That was recorded. We were in Vanuatu, and that was recorded in Sweden. And it was right around sunset where we were. And Sweden, basically the path it made a complete circle, and the guy in Sweden could hear us coming one way, and then the long way would come around a little bit later, and then they'd both continue on and would be echoed again.
So then the Earth and all the different layers of the atmosphere, they're depending on the different factors. That's the first antenna, right?
Essentially, the F layer of the ionosphere is giving you your first bounce. It's essentially providing you a reflective mirror of sorts. when dealing with ionospheric propagation, long distance.
So I guess, Scott, along that vein, if it's traveling around several times around the Earth, wouldn't I'm surprised it didn't fade
It
in.
did. It
Oh, it
faded.
did.
I mean,
Okay.
every time around it got weaker. But if you think about, if you start looking at the map, every trip around the Earth from the geometry gives you a maximum skip length of about 2,500 miles, and it's 24,000 miles circumference. So, I mean, we're basically talking 8, 9, 10 bounces just to get around one time.
Yeah, I sorry, I lost connection there for a bit, but so that would be due to propagation path loss, right?
Yeah, just the
Okay.
fact that every time every time it hits something, it has to bounce. And
Right.
so it bounces off the sky, it bounces off the land or the ocean, and then the sky again, and then the ocean again, and then the sky again, and then the ocean again. And by the time you're hearing the second trip around, it's already made 20 bounces.
Right.
So
Okay.
it was, I've never heard anything quite like that before.
Yeah.
And we could actually hear it ourselves. That the stations that were calling us were all echoey also. It was very weird.
And that was at one of the peaks when like the sun was the closest, you were saying?
That was 2 years
Yep.
ago.
An
We were
11-year cycle.
Yeah, we were in Vanuatu and it was right before the sunspot peak. I saw somebody's hand come up. No?
Sorry,
Okay.
that was me. I thought my question might be a little irrelevant
No
because,
such thing.
well, so my first question I was going to ask because Google wouldn't tell me the direct answer, but I had to word it differently because they've changed the whole AI settings. But my first question was the distance from Vanuatu to Sweden.
I'm gonna guess 5,000, 6,000 miles. 5,000,
It's
6,000.
it's over 10,000 miles.
Well, it depends which way you go.
Right. And so I was like, my other question was, you said that it like bounces from like, the sky, the ocean, like it just keeps doing that movement, and that's the whole time. Like that's
Yeah.
the so it does that for over, well, any distance that you put a call out does it for that distance.
Uh,
Does that
it well, it depends. If you start looking here, like we're gonna show a little bit about something called propagation right now and how this all works. Okay, can everybody see this map? Everyone see okay?
Yes, sir. Yeah.
Okay, so I have let my radio just run and listen all day. Let's see if it's even working. Oh, I don't want 6 meters, all bands. Okay, so in the last 15 minutes, my station, which is right up here, has been just listening and reporting everything that it's heard on a mode called FT8. And so notice what you see here. So I'm in the Pacific Northwest, right? Okay, a few folks in Southern California, but where are the bulk of them in North America?
Northeast.
Yeah.
Northeast.
Northeast, okay. And if you were to look at a distance, okay, and that would cover down to Florida, and there'd be a little bit of a range out here in Texas, but notice what is missing. And it's not that there aren't any people there. What's missing?
All the
Your
mountain
neighbors.
Yeah, all my neighbors. Why is that?
Bounce distance.
Yeah, but why?
Is
It's
it that
about
donut thing?
it's about it's about geometry. It's about geometry and the layer of ionization up in the sky. What happens is, in order to get any closer than, let's say, 1,500, 2,000 miles, the angle of attack at which the signals would have to be hitting the sky to achieve that, like from Denver to Eugene, there are lots of stations in Denver, and I can show you. Let's see, received by Grid Square DM79. I know that's Denver. Come on, come on, hurry it up. Still loading. Come on. All right, let's narrow it down. Oh, there we go. Okay, so notice the folks in Denver are hearing everyone, right? But they're not hearing me.
It's kind of like what we call in tracking submarines a convergence zone.
Yeah,
because of the geometry, like I said, the refraction of the waves and how they go when they come back down.
We call it the skip zone because it's essentially skipping over. Now, some of the folks in Denver are actually hearing a few folks from like Seattle, but the bulk of them are to the east. So we're basically, kind of ignoring each other. Whereas on the other hand, let me go to 17 meters. I think that's where I left the radio this morning. They're not hearing much of us. And let's take a look at what we're hearing. Notice we're right now hearing tons of Europeans that they're not hearing. And because the path is different, and you notice the day-night terminator, so who knows what big differences there are up there that are causing this to happen. And this map changes from day to day, from season to season, from year to year. I mean, spring to summer to winter to fall. It always looks different. It follows some basic general rules, but like right now, we should be hearing a ton of Europeans if I were upstairs listening on the radio. There would be a ton of Europeans, and sometimes you won't hear anything on the East Coast, and you'll hear Europe just fine. And then in a couple of hours, we'll be looking at this day-night terminator. Like right now, if I were to look at, let's say, who's on the terminator? Let's look at from Japan, for instance. PM. BJ4, oops, BG4 UVR.
So is that like, when you're shooting skip, you just never know what the conditions or.
You can guess, but you can't guarantee.
Yeah.
So like here, this is coming out of China right now, the station in China. And these are all the stations that are hearing them. And what would happen? What'll happen typically is that in a few hours, when this gray line moves a little further, is that it will be really good to the west coast of the United States because it's following along that day-night terminator. It makes for some very interesting stuff. Okay, another thing we do, let me unshare that. Another thing we do is we do something called E-skip. The E layer is that section of the atmosphere that is, oh come on, don't do that. Why is this thing behaving this way? Share, whiteboard. Okay, so I'm going to draw a rudimentary one now. D, E, F1, F2. Okay, the E layer is kind of a weird layer that is about 100 miles up. And this is where we get weird effects like sporadic E and meteor scatter and aurora. So 6 meters is kind of like the main band for this kind of weird stuff to happen. So that's 50 to 54 megahertz. And sporadic E is still unknown as to exactly why it happens. It seems to happen more in the summertime, and it seems to happen more above thunderstorms and areas of crappy weather. You basically end up with a really, really dense layer of ionization, like really dense, in one spot. And what ends up happening is that these people here can talk to these people here, and these people here can talk to these people here, and these people can talk to these people, and you can actually map out where the center is. It's a very weird propagation mode, and it comes when it feels like it, and then it disappears, and it may not come back for days or weeks. Meteor scatter. What happens is you end up with during meteors, during like the Perseus meteor shower, they typically, in entering Earth's atmosphere, they don't encounter enough of the atmosphere to burn up in the F layer. But when they make it down to the E layer, there's enough density that they cause ionization, and they cause these little tracks to form. And using very high speed Morse code and other modes that are extremely high speed, you get about 15 seconds of ionization up there where you can bounce signals off of the meteor trail. Auroral is exactly what it sounds like. You basically have the aurora, you aim your signals into the aurora at the North Pole, and you get a reflection coming back. And it's also very cool. I've done it one time in 41 years, or 40 and a half years.
Is the E in that? Is that a sporadic electron? Is that what that means?
No, it's just the E layer.
Oh.
There's the D, E, F1, F2. So I think it was assumed they started on D because they didn't know if they'd find something lower. So to my knowledge, they never have. Okay, so that is propagation. Propagation is basically how signals bounce around. So now let's talk about line of sight, because line of sight is actually really important for dealing with close-in things. And since a lot of us are going to be, I consider the VHF and UHF bands to be very utilitarian. I mean, I have my handheld radio. It's around all the time. It's good for emergency communications. Okay, so I've got my transmitter right here, and someone else has a transmitter over here. Line of sight literally means that there is nothing in between you blocking their way. So here are two people. Each of them has a handheld. They are line of sight to each other. So now we're gonna start messing with these guys a little bit. We're gonna put a hill. All right, there's a hill. They are no longer line of sight because there's a hill there. So what's something that if these people were just shouting at each other and there was a hill there, what could they do to be able to talk to each other? They could talk to one of their friends, and they could have their friend climb on top of the hill and do what?
Talk to you.
Talk to you. This person would talk to them, and they would repeat the message back that way, and then this person would talk back and repeat the message back that way. That would be a repeater, right? I mean, that would be the definition of a repeater. It's a person who's repeating something. All right, so instead of that, what we do is we take that person and replace them with, let them keep using radios instead of being people, and then we put a little tower up there that looks like this, and then we put an antenna on top of the tower, and we have a station that is now in automatic mode, so that this person can now transmit on a frequency. The system up there on top, if it accepts the signal, will simultaneously repeat that signal in all directions to everyone listening on that frequency, including this guy, who will then respond by saying, well, I know you can't hear me directly, but I can get to the repeater, which means that those signals are then sent out in all directions, including to the other person, and they can have a conversation. So this is a repeater station where it's on a mountaintop or a hilltop or a building or something like that. There is the published frequency for a repeater which is, let's say, 146.72 megahertz. I use that because I'm the trustee of that repeater. We specify something called an offset, which is negative 600 kilohertz or positive 600 kilohertz, depending on what frequency that repeater's on. In this particular case, it's negative 600 kilohertz. This is known as the offset. The reason that we use an offset is because if the repeater were receiving and transmitting on the exact same frequency at the same time, then everybody would have trouble being heard. Basically, the repeater would be interfering with everybody else and itself. So that doesn't work. When you transmit, your radio has this function which is called offset, which causes its frequency to change to 146.12 megahertz. So you are now transmitting on a different frequency. The receiver at the repeater is listening to your transmitting frequency and retransmitting it on the published frequency. This allows a large number of people to hear you. It also allows a large number of people to be able to engage in a conversation. Only one person can talk at a time. There's something else, which is kind of like a gateway for a repeater, which is a CTCSS, also known as a PL tone or private line. This is a system that allows you to transmit a subaudible tone anywhere between 67 and 254 hertz. It's a very, very low frequency, along with your voice, which is essentially used as a key to open up the receiver on the repeater up here. If that key is received, it will accept your transmission and then retransmit it automatically. So that's known as CTCSS. There's also something called DCS, which is digital coded squelch, which is a sequence that is followed instead of being just a continuous tone, which is kind of like a little frequency hopping tone that has to be superimposed on the signal. And if that's not there, and the receiver is looking for one, your signal won't be retransmitted either. All right, so that's how a repeater works. Now, there are certain times that you will not have a repeater nearby. Right? That is known as simplex if you're talking point to point. These two people, for instance, in mutual communications range are now talking point to point. There are some times that things will get in the way. There may be, again, a hilltop, in which case you don't have a good communications path. However, if you have enough gain, you can point your signal at the top of the hill, and this goes back to good old physics. Your signal will diffract over the sharp edge of the mountaintop. This is called knife edge diffraction. And it allows two people that are not within line of sight to talk to each other. There is also, depending on the frequency you're on, the possibility of, let's say there's a building over here. And you are over here, and somebody else is way over here, and you're not within line of sight of each other, you can actually bounce a signal, conceivably, if you have a little bit of gain, off the building and be able to be heard on the other end. So you can bounce your radio waves intentionally off of other objects. One of our club members a couple of years ago was up around Mount Hood, and to talk from Mount Hood to Eugene, he actually pointed his antenna at Mount Hood and intentionally used it to reflect signals back to us.
Is this also times when you'd use your rotor on your antenna?
If you want to aim it. I mean, I don't have a rotator, but if you have a rotator, then this is exactly when you do it.
Yeah.
Okay. Let's see other things. Let's see. We not only talk, we also do digital communications. If we look at, let's say, a signal coming from here to here, and let's put a building over here. Here's a building. So we have a direct line of sight between two people, which is great. Do radio waves always travel the shortest path? No, they don't. They follow multiple different paths.
Travel out in all different directions.
Yeah. So some of your signal will be going this way, and some of it will be going this way, some of it will be going this way, and some of it that hits this building may end up getting here at a slightly different time because it had a slightly different length to cover. So there could be two different signals of different strengths that are combining at the other end. So it is important at this point to draw the waves that look like this. By the time it gets to the end, we're going to assume that it looks like that. But this other wave, which I'm going to draw in orange, may arrive at an integer multiple, or at an even integer multiple of its wavelength, or an integer multiple, or it may arrive at some other wave. It may arrive at some other time. Well, what if it arrives and it's here? These are going to add together when they get there. What is, at this point, right here, the orange one plus the brown one? What do you see?
The high and the low, the peak and...
They're going to add. What's the sum of those two?
0.
Pretty close to 0. How about over here? It's not great. It's not bad, but if they're perfectly misaligned, if they're perfectly 180 degrees out of phase with each other and about the same amplitude, what you're going to get is this and this. What's the sum of those two?
I mean, that's 0.
That's
right?
0. Yeah.
Perfect.
Let's say you're trying to listen to somebody and that's the signal that you receive.
They cancel each other out, right? Resonance?
Signals completely cancel each other out. No, I mean, you're 180 degrees out of phase. And essentially, that is similar to what a set of noise canceling headphones does, except this is being done on radio waves. So what ends up happening here is that this is being caused by the fact that if I were to actually look at the waves that are traveling through space, they look like this. These other ones have the same wavelength, but they had more distance to cover. So when they got there, they both arrived. Maybe they were in phase and maybe they weren't. You can't move a building. What can you move?
The frequency you're receiving?
Not if you've already selected it with your friend.
The transmitter or the receiver.
What do you do with it?
You could
move it.
Move them out of the way so you're not getting that reflective energy anymore.
Well, it'll still be there, but maybe, because let's say we're using the 2 meter band. What's the approximate wavelength of the 2 meter band? Come on, this is
2 meters.
Not a trick question. That's right. It's about 2 meters long, which means that wave covers 2 meters, which means that if these are coming in 180 degrees out of phase, how much would you have to shift this one of them so that they're now in phase?
A meter.
A half of a wave, which is 1 meter, which is how far?
3.3? Isn't it 3 feet?
About 3.3 feet, yeah. So in other words, you take your radio and you literally move a couple of feet in your room and look for a spot where it's loud. This happens all the time, especially inside buildings, because there's a lot of reflections inside buildings. I mean, the room where I am right now, the craft room, this is particularly bad for working into our local repeater. I will typically have to move around until I find a nice spot where I can hear really well. If I can hear really well, I'll be using the same thing when I transmit.
So would it just sound like a little bit of an echo, or...
No, it's just just noise. The signal goes away. There's no echo. You can't, I mean, the stuff is moving at the speed of light. You just basically it's just basically canceling. So you want to go to a place where it's not canceling anymore. And what if this were on the 70 centimeter band? How much would you have to move?
Was that a foot?
About a foot, yeah. Literally just a foot, and you may hear it go from loud to quiet to loud to quiet. Now, there are other times when, let's say, you're on the edge of a repeater's range or something, and you're driving along, and you will hear somebody go clear and then noisy and clear and noisy and clear and noisy. Essentially, you're now in a moving vehicle. And this is known as picket fencing, because it sounds like you're talking through a picket fence. And that is caused again by constructive and destructive interference. Just shifting back and forth and back and forth and back and forth. The other thing is that if you are dealing with voice, you're basically just listening to noise coming in and out. Let's say you're doing digital communications, such as packet. Digital communications require a good, clear signal. So let's say that you and another person are trying to send data files back and forth, and you have destructive interference. What's going to happen to your data file? I didn't get it. Please resend it. And it may again be, packet loss. It might again be a difference of, moving the antenna a couple of feet in one direction. Okay, so with that, we're close to the end of today. I'm going to stop sharing, and I'm going to ask everyone to how about taking a 5-minute break?
Sounds good.
And I'm going to just recap where I am in the class and what page we're on, because at some point we start to merge back to, what the book is doing. So, all right, 5 minutes.
Finally, so that's cool. There's the car.